this morning. My name is Guy Tevet. I'm going to tell you some details about the workshop, and then I leave the stage for, sorry. And then I leave the stage for the really exciting part of the day. So this workshop is a joint work with those wonderful people from the Max Planck Institute for Informatics, the University of Alberta, and Tel Aviv University. And in this workshop, we are interested in anything regarding the motion synthesis and character animation. That includes the generative methods from the data collection and data representation through the architecture, the training methods, the various types of input conditioning, including abstract and multimodal inputs such as text and music, the evaluation methods, and the generative tasks, including control, interaction with the scene and with other characters. We have today great speakers presenting different aspects of motion generation and character animation from both the academia and the industry. And this is the schedule for today. You can scan the QR code and get the full schedule. And the talks are going to be 45 minutes, which will be 40 minutes of the talk and then 5 minutes at the end for questions. At the end of the day, 5 minutes before 12, if we will be on time, we are going to announce the winning papers. So if you are one of the accepted papers, please stay until the end. And then we are all going to move to the Arch building for the poster session, which will be until 1. So this year we have 9 accepted papers in a variety of topics, including two-person interaction, gesture synthesis, multi-text to motion, and RL with human feedback for motion synthesis. If you are one of the 9 accepted papers, you can recognize yourself in this slide. In addition, our poster session includes 13 more papers in the non-archival track. This track gives an additional opportunity to present motion papers that were accepted to the main conference, alongside with initiatives from the industry. Out of the 9 accepted papers, 1 was chosen by the committee as the first UMOGEN best paper, which will be announced at the end, as I said. And now we can move to the fun part. So our first speaker today is Daniel Holden. Holden is a machine learning and character animation researcher in Epic Games. His pioneering work on motion matching, deep learning-based motion synthesis, and function-phase neural networks have paved the way for the current innovations in the field. His insightful blog posts are handling practical topics in character animation and make them accessible for beginners as well as professionals. And on a personal note, his work deeply inspired me and motivated me to dedicate my PhD to character animation. So I'm super excited. So please welcome Daniel Holden.
All right, I think we're ready to go. Yeah, thanks again for the intro and inviting me. I'm really excited to kick off this session. Today I'm going to be talking about human motion generation for video games, and what that involves, what the challenges are, why it's an interesting subject. So first I'm going to talk a bit about the constraints for video games, which are very extreme. And then some of the motivation for why we should actually try and do machine learning and generative AI for video games. Talk a bit about control, which is the subject which interests me the most right now, and I think is the biggest challenge. And then very quickly, I'm going to conclude. So first about constraints. Before we get started, I want to be kind of clear about what I'm talking about today. So what I'm talking about today is really something like this, where you actually have a neural network running in the game, generating the character animation on the fly, and it's interactive, so you can control the character with a gamepad or something like that. And that's in contrast to other methods where effectively you're generating animation offline using some offline method, and then you're going to put that in the game as one of your animation assets, maybe for a cinematic, or maybe you're going to use the data to put into some other gameplay system. So that's not what I'm talking about today. Today, I'm talking about actually running the neural network in the game, generating animation on the fly. And here's a little sneak peek of some of the recent work I've been doing, which I'm going to talk about today. So here we have a character in Unreal, and the animation is being generated on the fly. And we can give different controls. So we can even give a target point to move to, or we can give a trajectory to follow. We can give a position we want to jump to. And we can also do things like give a position to go and sit down. And the interesting thing here is that all of these different behaviors are being generated by one neural network. So we can give all these different kinds of controls, and we can put them all into one network and generate all these different kinds of things we want. Okay, so first let's talk about constraints. So some basic kind of napkin math if you're working on a game. Basically, you're running the game at 60 frames per second. That means you have 16 milliseconds to finish all the work you need to do for one frame of the game. And you can divide that by maybe 5 subsystems. So we have AI, we have sound, we have gameplay, we have all sorts of different game systems in the game. Also, maybe we have 10 characters on screen, something like that. So we need to divide by 10. And then maybe we have like 8 cores, so we can parallelize some work. So we get to multiply that by 8. And that gives us very roughly, let's say, 256 microseconds per character per frame of the CPU time. And that roughly makes sense with the sort of budgets I've seen in games. So maybe it could be as low as 100 microseconds per frame per character. Maybe for a hero character, you get a millisecond or something like that. It can vary a lot, but that's the kind of rough thing you're dealing with in terms of computation constraints. Memory is also a huge constraint. So if you're targeting a platform like the Switch or a mobile, you might have 3 gigabytes or less of RAM. And this is a kind of rough breakdown, typical sort of breakdown you might see for a game in terms of all the memory usage of the RAM. And a kind of example budget, you might end up with maybe 200 megabytes of animation. That might sound like a lot, but that involves everything you need. So all of the kind of cinematics, any animations you need to play at any time, all the runtime data structures you might need for processing that animation data. And very quickly that can get very low. So for example, one animation system I was working on for a certain scenario, our game, we got a budget of 0.5 megabyte for that animation system. And we had to do everything we wanted to do in that. So it can be really tiny, how much memory you get. Another huge constraint is quality. So when you go and you get AAA production quality motion capture, the data is very good. So we usually have accurate fingers and toes. So you get all the fingers, you get the toes. Sometimes you might even have 2 toe joints to get some sort of twist. As you can see, the contacts are clean. So there's no foot sliding, at least no perceptual foot sliding. And we have no interpenetration either or floating. There's no noise on the data either, at least no perceptual noise. And it's at 60 FPS. So I think this is a random clip I pulled out of our database. And this was not a particularly, this was a very normal capture, which we ran through the normal processing pipeline. If we compare that to lots of the work on generative animation, often we're missing fingers and toes. We have some foot sliding or penetration. We either have noise or we have over smoothing. And sometimes the frame rate can be quite low as well, as low as 20 FPS. So there's a big kind of difference between these two levels of quality. And to try and hit the quality bar on the left is really challenging because that's what animators and players expect in the game. And a kind of a disclaimer to this is that I used to show a slide with, these pictures from the first GAN paper and the new one with a little timeline for how long it took to get to this huge quality bar, which is that things change very fast in machine learning. If we have high quality data sets and we can train large enough models, I think we can hit the quality bar. So it may just be a matter of time in this case. The final constraint to remember is that games often require unrealistically fast and responsive animation. So this is what a kind of semi-pro Fortnite player looks like when they're playing. So they're moving extremely fast. The character is running around and moving extremely fast and accelerating and decelerating and turning and doing all these things way faster than any human possibly could. So what does realism even mean in this sense when we're trying to generate animation for a scenario which is completely impossible for a human to do? As a sort of aside, why can't we just use the GPU? So again, if you do some napkin maths here, uploading from the CPU to the GPU can take 20 microseconds on some platforms. Downloading again can take 20 microseconds. Just issuing the dispatch, like the compute shader to run the thing, can take 10 microseconds. So if you're really on a budget, you might have blown half your budget before you've even computed anything. Also, you have to cool the GPU asynchronously. So you have to do something while you're waiting for the result to come back. But most animation systems, you need the result right away before you can actually continue. So you need to find some work to do in the meantime. And finally, how much performance benefit are you getting? So the graphics programmers, when they move their code from the CPU to the GPU, it can be 100 to 1,000 times faster. So unless you're getting that same benefit, they're going to be complaining because they're going to be saying, well, I could be using that time much more effectively than you. So given all those huge challenges, why even try and use machine learning and generative animation in video games? So I don't know if you guys have seen it. This is a Unreal Engine demo that was released a couple of years ago called The Matrix Awakens. And this is all running in real time on the PS5 in Unreal Engine. And you can just see the visual fidelity and the graphics are just completely mind-blowing. When I first saw this video, it completely blew my mind. It's just incredible the progress that graphics has made. And if we just take a frame here, we can see that with the technology they call Nanite, they're actually rendering every single bike chain, link in the bike chain is individually modeled for this bike. So that's the kind of level of visual fidelity which we're rendering with now. And also all the tread on the tires is actually geometric detail, which is being rendered. On the other hand, if we look at the animation in this demo, we can immediately see some problems. So here, I'm just sort of jamming around the gamepad stick, and we can see the character is sort of moving or shifting their weight in some sort of weird ways. Here I'm walking into this object and we can see the character just as a sort of kind of canned reaction to bumping into something. Here I'm sort of trying to mess with this NPC and we can see that he sort of twists around and he twists his neck in this sort of weird, unnatural way. And here we can see, well, we still have invisible walls in games. So we might be able to render every single link in the bike chain, but we still have an invisible wall, which you can't get past. And the thing is, these guys actually did a great job of this demo. This isn't like a bad animation system by any stretch. This is the sort of thing you see in many games. In fact, it's better than what you see in many games. But the point is basically that we're so far away from the equivalent of having every link in the bike chain individually modeled that we need to do something different in how we build animation systems. So my sort of thesis is this, which is that we don't have rendering equations like graphics programmers do. So we don't have a set of equations that we know correctly model the world as it is. So instead, we need to take a different route. And we can make real world data the foundation upon which we try and build our systems instead. And by that, I mean, say, motion capture data. And then with this real data, we can instead build data-driven models, machine learning models. And these we can have controls and conditions which the animators want and require to generate the animation at runtime. So this was some work I did in 2016 on basically trying to apply these deep learning techniques to animation data. And we can see that, yes, if we use machine learning, we can consume a whole bunch of motion capture data and we can build models of animation, and we can use them to generate animation which does what animators want. So here we have a whole bunch of characters following some paths on the ground, for example. And not only that, but we get a lot of the other cool benefits you get from doing deep learning. So here we showed that you can also do like style transfer in exactly the same way people do style transfer on images. So it looks like we really can apply machine learning to animation data in the same way that you can apply it to images. And probably more importantly than that is it scales up to very complex situations. So typically in a video game, the way you build an animation system would be a sort of handcrafted state machine and maybe blend tree with rules for how you blend different animations and stitch them together. And this very quickly can just explode in complexity once you try and make something with a lot of nuance and a lot of details. So this was some work we did in 2017, which really showed that you can just throw a whole bunch of motion capture data at these machine learned systems. So here we got a bunch of data for navigating over rough terrain. And if you set them up carefully, they really do adapt to these different situations in a way that you could never craft by hand. You know, if you tried to craft this sort of animation system by hand with a state machine and a blend tree, the complexity would just be too high. It would just be impossible to manage. And there's another technique which is very common in video games called motion matching, which is another sort of data-driven technique. And we showed that actually, because this is also a data-driven technique, you get the same scalability. So here we have this is the sort of motion capture we got for navigating rough terrain. So you can see the character here is trying to kind of strafe over all these different obstacles we set up. And here's what happens when you use this data with a motion matching system. So you can see we get all the same nuances and details here. So really the key here is not necessarily the machine learning part, but the idea of having a system driven by lots of unstructured motion capture data. So you can see here all these nice little movements and nuances. So I would really challenge anyone to try and build a system that can do this sort of thing with a state machine or blend tree. So in this same paper where we basically learned it's a neural network approximation of this machine learning, of this motion matching algorithm. And we showed that if you have small neural networks, you really can hit the sort of budgets required for game dev. So here we have, in this paper, we have 3 individual networks doing different things. And when you sum up their costs, you're getting an average of 200 microseconds per frame. So you can get within that budget if your networks are small enough. One cool thing about this is that these neural networks act as a kind of, is it off? Hello? I'll just continue.
Yeah.
I'll be loud.
I'm sorry.
No, it's all good. Yeah, so these systems can also act as a kind of compression. So here we have a whole bunch of motion capture data for a dog. And this is really interesting because you can't really get the dog to act and do exactly what you want. So we have a whole bunch of this unstructured data of the dog running around, but we can throw it into this motion matching system and get a really nice natural. Hello? Is it on? Okay. We can get a really nice natural animation system. And because we're funneling it all through a neural network, once it's trained, we can throw away the original data and we end up with just the weights of the neural network, which in this case is much, much smaller in size. Okay, we're back. Than the original motion capture data. So here's another example where we tried to push this kind of to the limits. Here we captured a big database of, I think it was something like 30 different styles of walking. And we trained one machine learning model on all of this data. And so from 600 megabytes of animation data, we can go down to just 16 megabytes of neural network weights. So we can also get pretty good in terms of memory. So to summarize, if we use motion capture data with these data-driven systems, then we get this kind of scalability in terms of the animation complexity. We also get out-of-the-box realism because we're using motion capture data. So we know that this should be real as long as it matches the training data, because that's what really happened in the world. And we can get a huge amount of compression. So that's really exciting because it means that maybe we can really, really capture a lot of data and put all of this data into these machine learning models and really learn something that can generate a lot of nuance and variation and detail. There are, however, some big problems with these kinds of systems. So one is that it's very difficult for animators or designers to control the system if they want to make changes. So if they see something they don't like and they think there might be something better in their heads, how can they actually translate that change into a practical thing they do to the system, like parameters they tweak or whatever? If they do tweak these parameters, how can they predict what it's going to do? And what's the iteration time like? Because if you have to retrain the model every time you make a tiny little change, and maybe that retraining takes a night or something, your iteration time is completely destroyed. And if you make a change that you then have to revert, you know, time can just disappear very, very fast. So what I've been looking at over the last few years is this problem of control and how can we give animators better controls for these sorts of systems. And I think to kind of understand the problem deeply, we need to understand the difference between direct and indirect control. So direct control is really like the artist directly controls how the system behaves. And as they change things, there's kind of like a one-to-one correspondence between what they change and the output they get. And I'll give some examples of this. And indirect control is more like the artists control the input to the system, but the system itself is actually a kind of black box, which they don't really understand how it's necessarily working, but they know what changing the inputs is going to do to the output indirectly. So here's an example from rendering. A specular map in rendering is very basically saying like how shiny an object is and how does it create these sort of shiny reflections, let's say. And so historically, specular maps were always authored in grayscale. So they were basically like a scalar value saying how shiny it is. But artists realized that when you have metal, the specular reflection should be the color of the metal itself. So if you have a copper part of an object, the specular reflection, it should be orange, like the color of the metal. So the sort of direct control solution to this, which lots of people did, was to let artists use colored specular maps. So now the specular map is not grayscale. Okay, I'll just shout again. It's colored, and you can control the reflection directly in the color of the reflection. The indirect control solution is that the artist provides the grayscale specular map like before, but they also provide a metalness map, which basically says which parts of this surface are metal and which are not. And then the color of the specular reflection is inferred from the combination of these two maps. So here's an example in animation. So we have something like animation layering, where the animators say they want to have a character running around and aiming a weapon at the same time. So the animators might come to the programmers and say, okay, we'd like to layer an animation on the top half of the character and keep the bottom half, because that's going to be the legs rolling around. And on the top half, I want to do the aiming. So the sort of direct control solution is to add a feature for the animators so they can layer an animation on the top and have an animation on the bottom and have a kind of separation of the character. The indirect control one is more like, okay, we're going to let the animators provide a set of aiming animations, and then at runtime, they're going to say where the character's aiming, and we're going to sort of infer what the animation should be like for the top half of the character. And the problem with this sort of direct control solution is two things. So one is that there's a fundamentally incorrect assumption here, which is that you can completely factor out upper and lower body animation. We know that's not the case, you know, as the movement of the bottom half affects the movement of the top half. So if you do this, you get what people sometimes call tank mode, where it looks like the top half is just completely disconnected from the bottom half of the character. And here's an example of some guys pretending to be characters in a video game with a sort of tank mode character. But I think the bigger problem is really that this isn't actually what the animators wanted at all. What they wanted was the ability to have the character aim towards some target. And they thought that the way to get there was to get animation layering added as a feature to the animation engine. But if we actually go back to what they really want and work on that problem, then it's going to be a much better result than just, you know, implementing feature requests. So indirect control, it's not popular, right? It's artists often dislike it. They can struggle to get the results they want, and the solution might not even be obvious. And even if it decreases the authoring burden, they still might not like it. So for the specular map example, it's easier to just have a metalness map and a grayscale specular map than to try and, you know, get the color from the diffuse map and bake that into the specular map. So there's actually more authoring involved in the old way, but they still prefer it because they feel more in control. So what I've been thinking about is how can we design indirect control systems for animators with these animation systems. So there's sort of like a very practical problem to start with, which is that when we design these kind of neural networks that generate animation on the fly in games, designing the control inputs usually requires some expert knowledge. So here's an example from a paper where a character is trained to basically play basketball. And we can see all the different kinds of feature engineering that needs to go into this. So we need to give a trajectory. We need to give maybe the relative positions of some of the bones of the other character, maybe the ball, its positioning, its velocity, these sorts of things, contacts. Here we have a character that can interact with props. And here we're giving like a voxelization of the scene. And here in this work, you know, we had a separate network for each one of these situations. So sitting down was one network and one behavior. Getting up was another one. Interacting with someone was another one. Just walking around was another one. So we had all these entirely separate systems for all these different behaviors. And each one was kind of designed carefully by someone who knew the system very well, usually a technical person. So One solution, or at least interesting idea, I think, is something that I call structured controls. So very basically, the way this works is that for each kind of different behavior we're interested in, like say sitting on a chair or pushing another character out the way, we specify the required control structure. And what I mean by this is, what inputs are we going to give to the neural network, and how are those inputs structured? From this control structure, we can automatically generate a neural network which can consume that type of structure. And then for each behavior, we also describe the control logic. So that means, what do we actually want the system to do? What do we want it to output? You know, how do we map from the inputs to the desired outputs? And then the fourth step is sort of the key one, which is that if we do all of this systematically, then we can make much more complex behaviors by defining them in terms of combinations of other behaviors. So the character you saw right at the beginning, who can do lots of different things, we've defined all the individual behaviors, but the final sort of control is basically saying, okay, your control input is either going to be a trajectory, or it's going to be a target point, or it's going to be the position of a chair. And we have this big kind of optional clause about what we're going to give it. And for each one of those sub things, it's going to do the specific behavior that was defined for it. So the first step is each behavior needs to define a control structure. So basically what I mean by this is, we're going to say what sort of inputs are going to go to the neural network and how are they sort of arranged. So if we have this case where the character is moving towards some target point, and maybe we have a facing direction associated with this point, then our control structure might look like this. We're going to give the current pose of the character, i.e. the bone positions and velocities. We're going to give the target position we want to go to. We're going to give the target direction, but this is going to be optional. So that means maybe we will or we won't specify it depending on whether we want that. And we're going to give the desired gait. So do we want them to be running or walking or that sort of thing? And that was kind of a diagram. Here is how it actually works in Unreal. So this is using Unreal's Blueprint visual scripting language. So it looks pretty hairy, but basically the way to read it is to say, okay, the control is made up of the pose here, a target location, and optionally, so we have an optional control here, a target direction, a desired gait, and we also actually have another property here, which is kind of like the time until arrival, how long you want it to be till the character gets to the target. And this is exactly the same thing, but in C++ instead of the visual scripting language. So it looks a bit simpler in C++. And that's going to be our sort of API for how we specify the controls. And we can store that structure just as data. So you could imagine it being stored as like a JSON dictionary or something like that. So the second step is we need to take this kind of schema of the controls and generate a neural network, which can slice up all these different input variables and run them through some specific neural network structure. So you can think about it a bit like this. We take this kind of schema, we generate a specific neural network, which can consume that kind of structured input. So the basic way this works is that there's a kind of minimal set of different operations. And all of these different nodes here, we can basically define in terms of these kind of minimal set of like neural network operations, like concatenation or doing a matrix multiply or whatever. So in this case, basically we have, okay, the null control. This is just an empty vector. We could have a continuous control of some fixed size. So say we want to give a position. This is like a 3-dimensional vector. We have an AND. So this is going to concatenate a whole bunch of sub controls into one. An exclusive OR. So this is kind of saying, okay, either I'm going to give this control or I'm going to give this control. And the way this works is we have separate encoders for each control in this clause. And then we append a one-hot mask saying which one was given. We also have an inclusive OR. So this is where we saying, okay, I might give this, or both of them, or neither of them. I'm going to give some sort of combination of these subcontrols. And for this, we have some attention mechanism. We also might have an array of controls. So we're just going to concatenate some sort of fixed sized array of the same type of control. Or we could have a set. So I could say, okay, I'm going to give you a set of positions. They don't have a particular order. I might give you 5, I might give you 10. And again, we can use attention to take this set and encode it as some vector we can pass on. Once we have this minimal set of operators, we can define all the other controls we like in terms of these. So like I said, a location could just be a continuous control of 3 values. We could also do the same for a rotation, and we handle the rotation encoding properly. Scale, and we could say, okay, a transform, if I want to give a transform as input to the next network, that's like the AND of a location, a rotation, and a scale effectively. And we can define these in Blueprints or C++. Or here's another kind of interesting one, which you saw, which is this optional control. So you can think of the optional control as an exclusive OR between some other control and the null control. So either saying, okay, either I'm going to give this, or I'm going to give just the empty vector and give nothing. And you can see exactly how this is defined in C++. So here's another sort of example for the trajectory following case. So here's how it looks in the Blueprint scripting language. So here I'm saying, okay, for this behavior, I'm going to give a pose, a trajectory, and a gate. And you can see here I have a pose control, trajectory control, and an enum for the gate. And the pose control itself, you can see it's just defined in terms of a static array of locations and a static array of linear velocities. So a pose, it's just an array of bone positions and bone velocities. And similar for the trajectory, it's just an array of locations and an array of directions. So you can see how you could build up very complex control inputs in terms of these more basic types. So that's how we generate the neural network. Now we actually need to train this to have the behavior which we want. So in this case, we need to specify the control logic, which is basically saying, given this input, what should the output of the network be? So for the example I showed you before, the way we describe this behavior is in terms of a motion matching cost. So what this means concretely is that we take this input and we try and find a segment of animation in the database which is as similar as possible to this input. So say I give a trajectory, I would search the database for a segment of animation with the most similar trajectory to what I gave. And this would be the output segment, which we would ask our neural network to output. We'd ask it to just output that segment directly. So like before, we can actually specify this logic using the Blueprint visual scripting language in Unreal. So non-technical users can specify the logic they want associated with a particular input. And again, this looks fairly hairy, but if you break it down, it's relatively simple. Basically, we're checking, okay, given the bone positions, what's the nearest, search the database and give me the cost for every frame in terms of what's the most similar bone positions. And then we're adding up all these things for the different features and then finding the one that overall minimizes the cost. So once we've specified the logic, we have this final step where we can specify more complex behaviors in terms of these other behaviors. So for the demo I showed you, essentially we have a whole bunch of different behaviors going into an exclusive OR. So we're just saying, okay, either I'm going to give trajectory, or I'm going to give a target point, or I'm going to give a chair, or I'm going to give a jumping location or whatever. And the control logic is basically going to see which one you gave and dispatch to the different little subroutine which was defined for each one of these. So if I gave it a trajectory, we're going to go and call the function which finds the closest trajectory in the motion database, and that's going to be the segment we output. And this is how it looks in the scripting language. So a sort of overall view, as you can see, it's something like this. We have all these sorts of different inputs we might give. They're going to get combined together, and they're going to go into this neural network that's trained to output the segment we want. And this control logic, this matching function, is kind of like our loss function, where we're saying, given this control, this is the segment. And so again, this is the video I showed before. So here you can see, yeah, I can give a target location. I can also give a facing direction too, if I want. And I can give the trajectory. And I can also switch at any point between the trajectory and a different control, like jumping or moving to a target. And the character is just naturally going to adapt to this change. All right, so this whole system which we've made for the controls, this is actually generic, right? This doesn't necessarily have to be used for animation. So we have a reinforcement learning plugin in Unreal called Learning Agents, which you can check out. It's released, there's a bunch of documentation online. And it also uses this very same system to specify what the observations are going to be like for your agent. And also we have a similar system for what the actions are. So you can say, okay, either my action is going to be this or that. And if it's this, then it's made up of these subcomponents, like either I'm going to shoot at something or I'm going to move. If I'm moving, I need to pick a speed and a direction. And you can break down your actions in terms of this big structure. So here's some examples we used for testing this. So here, an agent is learned to go to the green balls and avoid the red ones. And it's using the set observation. So we don't know exactly how many green or red balls there's going to be. Here's just a little game where the character tries to catch this gray ball. Here you can see some ray casts. Here we have some agents that are trained to drive around this track. And here we have a Connect 4 game where it's doing self-play against itself. So you can think of this a bit like, okay, our matching function we had before where we had the control logic. Now instead we have a reward function where we say, okay, for this particular control input and this action, what's the reward going to be like? And instead of outputting animations, we're outputting actions. So like before, we can specify this reward function in the scripting language in Unreal. And you can see it a bit like this, right? So we're going to give as input, say we were driving around the track. We might structure our controls like this. We're going to have an array of positions and directions for the future part of the track. Maybe we have the current speed we're going at. And maybe we have a set of observations for all the cars surrounding us where we're going to get the relative location of that car, its velocity and direction. And then we train this policy to make the correct action using the policy gradient and PPO. All right, so that is basically it. So yes, human generation for video games, it's still very challenging. We have a huge number of very tough constraints, but that also makes it fun, makes it a fun challenge. And we've got such a long way to go in terms of realism that maybe this is the only path that is realistic or open for us to take. And I think it's really important that we understand the issues of indirect control and try and build tools that animators and artists and designers can actually use and feel like they're empowered to use, and they feel like they have some notion of how things are working. So yeah, thank you very much.
Question?
How much important is for the goals and shapes laws that's what we are going to ensure that like the level of plausibility is.
Yeah, that's a great. So the question was, how can you ensure that the pose is plausible and how important that is in motion generation? So I think in terms of video games and VFX, it's incredibly important. So even motion capture data or data that looks very, very realistic, animators and art directors will have feedback on that and ways they want to change it. And so if you can't hit the sort of plausibility bar, then it's already not going to be very useful for people. And you need to hit that first, and then people want to start doing art direction on top of that. So I think for video games, the quality constraint right now is probably still the biggest bottleneck for these methods and using them practically in video games. So as you saw, we can hit the performance, we can hit the memory constraints, but getting something that looks really great and reacts really well and which people can art direct and control, that's the biggest challenge right now.
Continuing with thread of plausibility, I think another aspect is the dynamics of human body motion. So how is the animation industry looking at this? Or is it something that roboticists should worry about?
I think the dynamics, people are really interested in it and doing more physics-based stuff. They'd love to do that. I think we're at the point now where games can afford to have some level of physics, whether it's pseudo physics or fully simulated. Again, the question usually comes down to the controllability and the art directability of physics. Because if you're in a situation where you see something you don't like, but you don't have the ability to correct for that, you're kind of stuck. And what tends to happen is people go on the conservative side and they switch back to the systems they know. Yeah, I think if we could have the controllability there, people would be very open to physics-based approaches in games.
For human-like realism, how much data will you become? How much multi-classes and what is the evaluation that you expect, and also the capability of classes? How many humans will go to one human to another?
Yeah, so I'd say a kind of ballpark figure, for example, for the stylization we did, if you want to just have, say, walking around, then I'd say minimum you need 5 to 15 minutes of data to get something good for these sorts of systems for one human. If you want a different style or a different character or a different gait, you need to multiply that up. So it does grow like combinatorially very, very fast. So it's very important that your mocap pipeline is efficient enough to handle that much data if you want to try these approaches. So for example, the system you saw I showed today, there's at least an hour of motion capture that is trained on.
And then what happens with it? What holds the weapon I saw that. So the human computer and poses the structure and the body ratio. So how do you reflect that? Because if it's based on blind data driven, it's just learn that manifold of movement from the data, whether and from the motion capture, which actually is good. So how do you reflect that with the body?
Yeah, so practically, the solution that's normally done is retargeting to 1 or 2 canonical bodies. If you want to have body variation, then yes, there will be some variety in your motion capture data. It may be less than you expect. However, if you want very stylized motion for characters of different body proportions, then you will get different motion capture data. You will need to multiply that out by how many combinations you want, and maybe once you have a variety, you can interpolate between them to some degree, something like that. Yeah. So it's still kind of very early days with this stuff. We haven't tested it like super extensively with artists in the loop. I mean, it's definitely a lot better than previously, where essentially technical people were hand engineering features. So now you can set it up in Blueprints if you have some technical skill, you know, some minimum level of technical skill. You can script everything in Blueprints. So that's definitely unlocked a lot. But especially for learning agents, reinforcement learning is very, very challenging for people who are not experienced in the domain to get things working. So it's still a huge ask for people to say design reward functions if they're not technical and have no experience in reinforcement learning. So I think part of this idea is that we can have presets made up of smaller pieces. So here, for example, I had a pose control, which I designed. And if there was a non-technical person who wanted to give a pose as input to the neural network, they could pull in my pose control, and it's going to, for example, encode the rotations in the right way so that they don't need to know about this sort of detail. They can say, I want to give a pose as input. Here's the library of controls. Here's the pose control. Put it there and go from there.
Take just last question.
Okay.
Hi, thank you for a great talk. How can you combine the system like styles? Like the other you mentioned, you could go, or you create another style and copy.
Yeah, I guess it's up to you. So you could either have a variable which you put right at the end, which says the style. And assuming you have, say, style data for your different behaviors or whatever, you could set that or not set that. It could be an optional variable, let's say, for whether you want to provide a style or not. So you could do it like that, or if you wanted to embed it in the individual behaviors, you could also do it like that. It kind of depends how you want to control the system and how your data is set up, I think. Yeah, so as an extra control, you could put the style you want, and this could be an optional control. So data where you had a particular style, you could provide what that style was, or data where you didn't have any particular style, you could not provide this control. And then hopefully the system would learn what it means when you have style provided and when you don't, and how to adapt it to different styles.
Okay, so let's move on to the next speaker. So let's thank Daniel again. Apologize for the on the way, but for now we will do the
Oh no, it's okay. I'll sit here.
Okay, so thanks very much. I'll talk loud enough, hopefully, that you can hear me. If you can't hear me in the back, just let me know. Unfortunately, I have audio on my slides that may not come through, so we'll just deal with that. So we gesture all the time, and we gesture when we communicate with people, we observe people gesturing, but unless you're a gesture researcher, I don't think we think very much about gesture. And so I wanted to start off by showing some examples of how complex gestural behavior is to kind of set the bar for what we're trying to model, because I think we're actually a long way from achieving the kind of complexity that people achieve. So this is a study we did a few years back. We put people in motion capture suits and then we projected them into VR and they interacted in VR. Here they're discussing apartment layout. So you can see the real person, the projection of the person in VR. But what I want you to pay attention to is the gestural behavior. And we saw fairly complex spatial communication. This was a grounded task, so they had something to refer to. So these are some examples of that. And we also saw effective communication or communication of emotion. Okay, so what we found out was embodiment, or what is sort of widely known, embodiment is a powerful driver of both social presence and of communication. And so the question is, can we build systems that can synthesize this kind of rich behavior that is actually communicating affect and communicating function? There's been two general paradigms in trying to do this, and this is work that goes back 35 years now. The early work was based on rule-based generation, and the idea here was that you would take some form of input. It was generally text, but could be audio, but most of the early systems were based on text, and then you pass it through some rule system. So you do some analysis of the input language, you have parts of speech, you can tag different words, and then you build rules that will map that to particular behavior, and then you output a list of behaviors that you want your character to do, and then you generate animation off of that. Recent work has instead been exploring data-driven gesture generation. And this is something that I started working on about 20 years ago with Michael Kipp. And at the time we were using fairly simple statistical models, and now this is being moved to deep learning. So again, most systems will take either audio or speech, pass it through a network, and now they're directly output motion. That's supposed to align with the speech. And so you're generating co-verbal gestures that go with the verbal presentation of the character. So the basic architecture of most of these systems is that you have audio. Some will also take in text, but most systems will take in audio as their input. You pass it through some kind of deep learning network, and you output frames of animation. So the audio is represented. There are different representations. The mel frequency Kepstrom coefficients are very common. People use pitch. There are other representations that people have experimented with audio as well. And the output is simply a pose at each frame. And that pose, depending on the system, could be joint positions or joint angles. And so you're going directly from this input signal to output motion. One thing that I would mention is these systems generally take future information. And so they're often doing this input on an entire utterance. They're not necessarily doing this in real time. This is a very challenging problem. And I think maybe my main takeaway from this talk is to hopefully get you to understand some of the challenge. Gesture is idiosyncratic. So that means that different people gesture very, very differently. It's also not well represented. For language, we have a nice way of codifying language. We have written text. We don't have anything comparable for gesture. There's a many-to-many mapping. So for any sentence that I utter, there's a whole set of gestures that would be reasonable. There are also gestures that would not be reasonable. And for any gesture, I could use that with multiple different sentences. So we have this many-to-many mapping to deal with. Can everyone hear me at the back? Yeah, okay. We're sort of addressing the data side of things, but traditionally there's been a paucity of multimodal data. Really good data of people gesturing is limited. A lot of the early systems had quite low motion quality that they could synthesize, and this is something that we're doing better at, but still there's room for improvement. It's difficult to control these systems. This was a question that came up in Daniel's talk, like, what if I want a character that is going to be really sad and then get angry, right? How do I put that kind of control into a system? We're still a long way from being able to do that. One of the biggest challenges is what I showed you at the beginning were examples of gesture that had really rich semantics. There was clear meaning in what was going on. Even if I didn't have the audio, you could read a lot of information in that. We're not very good at capturing semantics well in our synthesis systems. And our input data is, if all we're using is audio and text, it's quite impoverished compared to the full context that we deal with when we're interacting with people. Okay, so I'm going to look at 3 different approaches that we took to try to solve some of these problems. Some of this is older work, some of this is a bit more recent. The first is looking at the data issue and looking at the motion quality issue. So this is work that I did with Ylva Firstall and Rachel McDonnell. It's from 2019, so it's a bit of an older system. But the first thing that we were trying to do was build a better data set. And so Ylva was working in Ireland at the time, had access to wonderful subjects that can tell stories for hours on end. And so we put together 5 hours of motion capture of just a single person talking. And so we sort of deal with the issue that different people talk differently. So we have a really nice data set of this person talking for either 5 or 6 hours. And there are 2 ways that traditionally this data is captured, either using motion capture, which is what we did here, which is still, I would say, the highest end data you can get. More and more people are looking at using computer vision processing, and we use that in some of the other work, and that obviously scales up more easily. Quality is still very high. So at the time, this was 2019, we were using RNNs, we were using GANs. And what you get with a GAN is this is a plot of the real motion. So this is what the person actually did. We pinned the root of the character, but this is just the movement of their arms. And if you train on mean squared error, you get something like this. You get this very damped version of the motion. You're losing most of the expressivity of the actual motion. And so what we're trying to do is kind of put that back in the system. So we're looking at how we can force this particular architecture to do better on this. And one of the ideas that I had is that gesture actually has a grammar to it. Can I shrink this somehow? Okay. On my glasses. High floating medium controls. Okay, perfect. Thank you. Thanks. So gesture actually has a grammar. It has a structure to it. And what I was seeing in the output was it didn't have this structure. It just had this sort of like continuous hand movement, and it didn't have the structure that actual gesture has. And so we were trying to force the system to learn this kind of structure. So a real gesture will start with a preparation, and the preparation just basically brings the hands to the position where the gesture should begin. Then it has the stroke, and the stroke is kind of what we think of as the gesture. It's the meaning carrying part of the gesture, right? So here, this is a television host we worked on way back, but he's kind of bringing his hands up and then he's doing this fling down gesture. And so it's the fling down that really carries the meaning, and that's the stroke. And then it has a retraction. Basically everything but the stroke is optional. So people will go from one stroke to another stroke, but people will also do this kind of series of phases. And so we're trying to force the system to have that kind of structure to it. And so we did a whole bunch of labeling, and then we trained a phase classifier that would automatically label the gesture phases. And we used that as one component into our adversarial loss. So we have this phase classifier, and it's going to measure the phase structure. And that's one of the components that we use in our adversarial loss. And I'll show videos of the others. But this is an example of the phase classifier. So you can see at the bottom, it's doing labeling of the phases. So this is what we were kind of able to train a system to do. This is actually a fairly hard problem. It's a fairly hard problem for people to do this labeling, but we were able to get reasonable performance. And then this is just kind of looking at if we leave out different discriminators. At this point, we were using position data. The motion realism discriminator enforces a length constraint. If we leave that out, you get just kind of nonsense. If you leave out mini batch, it just finds the solution it likes and keeps doing it, right? So it's just going to keep kind of playing in this one space, and so you don't get much divergence in your data. Without displacement, then you get this really jittery motion. But if you put the whole set together, you get something that is sort of vaguely gestural, I would say. I think this is a hard problem. We've got a long way to go. I would say a lot of systems do something that is kind of like this. They time fairly well with the audio, but they don't do a very good job on meaning. And we're getting better at that, but there's still a long way to go. But if you look at our plots of the output, we were able to produce something that was similar, although still a long way from matching the real output, but very different if we leave out these other discriminators. Okay, so that was sort of our first foray into trying to use deep learning into this space. The second approach that I'm going to talk about is work we had at SIGGRAPH a couple of years ago, and it's really addressing this issue of control and how you can put better control into these systems. Again, we have the same basic architecture, and the idea is to add in a control signal to our input. So just have a richer input representation. And it's based on an idea from video games, the idea of motion matching. So if you're not familiar with motion matching, the idea basically is that you take some sequence of motion, you take some control input, and you use that as a query into a database to find the next sequence of motion that matches the control and matches your current pose. So you get continuous motion that reacts to the control input that you're getting. So you use this kind of lookup technique for querying motion. And so you're using little snippets of motion, and because you're using little snippets of motion, you're going to get something that's reasonably high quality. And so what we wanted to do is we wanted to use this with audio and then with animator controls. And so we have both audio input and we have controls such as make the left hand slow, make the left hand further from the body, raise the height of the left hand, fairly low level controls. And we did a very simple search. We just did a KNN search based on these controls, and we output motion. Then in a second stage, we pass it through a network that basically does some cleanup on the motion and slightly refines the overall quality of the motion. So we have our audio signals. We use the Mel frequency Kepstrom coefficients. We have our gesture data. We use positions. We put those in the database, kind of have our query motions. And then how this works in practice is we have our audio. And as I said, we're generally assuming some future audio. So we have some future amount of audio, and we have our current pose. So our input is the saturated color. So we have some future audio. We have the initial pose that we select. And based on that, we select end candidates based on pose similarity. So all of the end candidates will transition reasonably from our initial pose because we cause them to be close to that pose by design. Then for each candidate, we compute a pose and an audio distance. So each of these end candidates, we look at their distance based on audio match and based on pose match. And then we select the one that has the lowest total rank. So if something comes first in audio but comes 20th on pose, that's going to be a bad match, but something that comes second and third is going to be a good overall match and becomes the candidate that we use. And then we simply take that candidate, we concatenate it to our output, and then we repeat for the next audio sequence. And we go through like that. What's really nice about this approach, it's very simple and it allows a very simple way of putting control on top. Essentially what we can do is we can allow the user to put in control vectors that basically say, is a particular feature present or not, right? So that feature could be, again, like the left hand is high, or I'm using my left hand, or the left hand is fast. So these kind of low-level criteria, and they just basically mask when in the motion they want those criteria by putting ones in those masks. Then all of the data in the database is labeled for these criteria. So they're marked as either present or not. And then we simply do a prune. So we run exactly the same algorithm. We don't modify the algorithm at all. We just drop out all the data that doesn't match these criteria. And as long as you have a reasonably large database, this very simple technique works, and it gives you good control over the motion, this low-level control of the motion. This is the refinement structure. Again, we pass it through again as the second pass. I think it's important. I'll show you some examples. I should mention Ixnul Habibi was the lead author on this. Here are some examples of control. So it's fairly low level control still, right? Like we're a ways from being able to say, I want the character to be melancholy, but we're able to build in control in sort of a reasonable way. Here's another control example, same sequence. And then this last example, I'm going to show that kind of falls out of having this fairly simple framework. What you can do is basically semantic copying. So if you have an example of a semantic rich gesture, you can basically insert that into this framework. And because it's a fairly simple framework, it's straightforward to do that. So we can copy that but, and then we can put it into future sequences. So this is potentially a way to scale up semantics, right? You could introduce more of these labels, and then you could have a semantic layer of control on top. Okay, I'm going to skip this for time. We compared it to some other systems. It performed fairly well. But what I want to talk about is one last approach where we were kind of looking at this fundamental issue of, can we actually generate meaningful gesture? And so here we were looking at this issue of both having impoverished data. So we wanted to see, okay, dealing with just the data that's out there, can we actually generate reasonable semantics in the kinds of systems that people are looking at now? This is a really nice figure from Stefan Kopp, who's a kind of well-known gesture researcher that I think many of us feel is sort of an accurate depiction of the field. So this is how effective the communication is. This is how realistic the motion is. And these early systems, this happens to be one of his, but there are a bunch of us that were building these early systems 20 years ago. They actually communicated reasonably well because they were using rule-based systems. So lots of issues with that, but they would actually communicate fairly well. Motion quality wasn't great. And what we're seeing is improved motion quality, but probably less meaning. We're seeing kind of a lot of sort of hand waving that's not very meaningful. And then the question is, can we basically go up this curve, right? So we want to be able to push this up so that we have really meaningful gesture that also looks really good. So what we were looking at here was basically kind of taking inspiration from these earlier systems that would kind of predict particular gesture labels and saying, can we predict features that we want the gesture to have? So if we're going to predict semantics, can we at least predict the features of the semantics? And then we could have a second network that would take those features and take in the speech and text and hopefully put out meaningful gestures. And so what I'm going to look at here is just this part of the system. Can we actually predict features that we want? And we set a lot of constraints on this. We wanted to use data sets that were sort of readily available today, that were sort of reasonably small. And if we can do this, then probably we can actually synthesize meaning in our gestures. If we can't, we need to sort of rethink our approach, right? And we need to think about completely different ways to tackle this problem. So we were looking at two different challenges. We wanted to predict two things. Simply, does a gesture occur? So if I give an input sentence, does the character gesture? And when in that sentence does the character decide to gesture? And then predict a bunch of properties that that gesture should have. So we have these two different output goals. Do we have a gesture? And then what the properties of that gesture are. And we trained it on a data set from the BFL group in Germany. It's a bunch of people looking at tours of a VR world. It's about 4 hours, 25 different subjects, and then they're asked questions like, where is the church? And they'll say, oh, well, you go down here and then you turn left and there's the church. And what does the church look like? Well, it has a steeple. And so they're fairly rich gestural examples of this VR world that they've gone through. And it's a richly annotated data set. It's probably the best annotated data set, at least that we're aware of. So it has the gesture categories. So is it a pointing gesture? That's a deictic gesture. Is it a beat gesture? So beat gestures just kind of keep timing with the audio, but don't really have any meaning. Is it an iconic gesture, which creates a sort of representation of something? Does it modulate the discourse? And then it had the thing that we really care about, some information about gesture semantics. So does it describe the amount of something? Does it have shape information? Does it have direction information? Size information? And then it had the gesture phase information that I talked about earlier. And so we were looking at if we could predict each of these different kinds of properties. The problem with this work is it's very difficult to evaluate. There's no kind of previous system that we can reference and say, okay, are we better or worse than that system? And it's a difficult task even for a person. If I gave you a sentence and I asked you, okay, what properties should the gesture have for that sentence? That's a difficult task, right? So what we did instead is we decided to compare against simple bottom line systems, right? Since there's nothing out there, we need to say, okay, can we do better than some simple prose systems? And so what we looked at was always predicting 0. So the thing is just not present, always 1. The thing's always present. A uniform random or an informed random, which is basically weighting the random distribution based on what we actually saw in the data. So it's sort of a fair random test. And that's sort of our main comparison point. And what we used was the macro F1. So just to kind of, if you're not familiar with the terms, precision is the proportion of actual positives that are correct. Recall is the proportion of actual positives that are identified correctly. And then F1 is just the harmonic mean of those two. And macro F1 is the harmonic mean of predicting that for all of your cases. So our cases here are present and not present. And so we use macro F1 as our measure. And you can see like always 0, because these things are relatively rare, always 0 actually performs relatively well. But on macro F1, it will drop down. And so we're able to predict something that is kind of outperforming these base systems. So in terms of gesture prediction, we're fairly good at predicting whether the gesture should occur. And the text is actually very indicative of whether or not we should have a gesture, which is interesting. It outperformed the audio in our test. We can predict which properties in some cases. So we're reasonably good at predicting pointing gestures and iconic gestures. Beat gestures were basically at random. Most importantly, we can predict to some degree the semantic properties that need to be in the gesture. So we can say like this is an appropriate time to have a direction gesture or a size gesture or a shape gesture. And even if we're not doing this perfectly, if we can do it some of the time, that allows us to add value to the output, right? Because if we have a bunch of gestures that don't mean anything and we make 40% of them meaningful, that's a huge difference in terms of the utility of that system for a user. And we can predict stroke reasonably and prep reasonably, preparation, which are the two kind of most important phases. The others are more kind of at chance level. So the takeaway was that it is possible to predict some of these properties from speech. For predicting gesture categories and gesture semantics, only the text is needed, which was really interesting. And for gesture phase, then the prosodic features are really important. So the audio is really important for gesture phase. And as I said, this, even if it's not performing at 100%, it will allow us to increase the utility of these systems by producing some meaningful gestures. Okay, so we only looked at one data set in this. We only considered a few deep learning architectures, so lots of limitations. And there's a fair bit of annotation work to build this data set. There's probably ways to build this more automatically now, but there's a fair bit of annotation work necessary to build a system like this for training. And then the question is, so if we do this, can we build this second set of the architecture, and will it actually produce more meaningful gesture? And is this a way to move forward to produce sort of more meaningful gestural output? Okay, so I want to kind of close by talking a little bit about some of the challenges. One of the huge challenges of this is evaluation. There's a lot of interest in doing automated metrics, numeric metrics, and of course they have huge advantages. To date, they have not proved competitive against human judgment. So human judgment remains the kind of gold standard for evaluating gesture work, but that's obviously slow. It's also very hard to measure what we really care about. Like we want to know, does the sequence have a particular semantic content or not, right? That's a difficult thing to measure. There's a really great, let me give a plug to this really great challenge that's been put out, the GENIA challenge, where people can submit systems and they compete with all the other systems submitted. They use the same data set. They run the evaluation for you. So it's a really nice way to potentially move this field forward. Data sets are growing, but they remain small. Tiny compared to text, but small compared to even other motion and image domains. The idiosyncratic nature of gesture is a problem, also the varied context, right? I'm speaking differently because I'm in front of a room, right? And I have an audience and I'm adjusting to that audience than I would be speaking at home to my wife, right? And so context is really important. Spatial context is very important. And so we need richer data sets that include that. Grounding is probably, to my mind, the biggest issue, right? So all of these things affect how we gesture. Temporal information, semantic content, who the speaker is, what their personality is, what their emotion is, what their style of speaking is, how the person they're talking to behaves, right? So is the person sort of disinterested? Is the person engaging with them? When are they gesturing? All of this has a huge impact. And then also the spatial information, right? So the spatial layout, both what's in the environment is important because we often gesture to objects in our environment, and that's part of how we create meaning. We also gesture to people in our environment, right? And so all of that spatial information needs to be in our data sets. Almost all of our data sets are of one person talking to a crowd, right? So there's a huge amount of work that needs to be done there. Finally, we're starting to see work that's leveraging some of these foundational models. There's a lot of work to be done there in leveraging LLMs and other foundational models. Okay, that's it. So I'd like to thank a very large set of collaborators. And sorry, the last system, the lead author on that was Taras Kucherenko. Yeah, I'm happy to take any questions. Yes. Yeah, I mean, this is the potential, right? So the question was like, can we use internet scale data for doing this? And then we'll have this big leap, right? This is the potential. So the largest data set that I know of is based largely on TED Talks. So it's the PATS data set. And basically they take these talks, they run them through a 2D joint locator, and then there's work that's been done at the MPII in Saarbrücken that will lift that up to 3D, right? That's a relatively large data set, but still small, right? Yeah, I don't really have a great answer to this. I think there's a huge amount of potential there, but there's a huge amount of variability, right? And so that's sort of what comes to mind as the challenge, right? Is how do we categorize the variability, and we should be able to build that into our learned systems, right? But I think that's a very big challenge, is how we sort of categorize the variability in the data that's out there. So it's both sort of the 3D tracking challenge, which we're getting really good at, but also the variability of the data, I think, needs to be taken into account in how these systems are built. Mhm. You mean using this as a data source? Uh-huh.
Yeah, so use it as a data source.
So detecting hands with like egocentric cameras. So the hand tracking stuff is well outside of my expertise. It is potentially an interesting data set, right? So you could potentially, if you had consent to build data sets this way, you could potentially build interesting data sets if you had VR chat systems, right? So potentially it could be an interesting way to build a data set.
Michael, thanks a lot for this wonderful talk. I want to get your perspective on what you think of when we work on motion synthesis as the target task. Like, do you want to drive a photorealistic avatar from the synthesis that we do of gestures, or is it something else? The reason why I ask is because now we have video diffusion models
Yeah.
that can animate us directly in a video space, right?
Yeah.
You may need some 3D a bit, but you don't need to actually synthesize proper nice human motion. You can directly do this in the video. What are your thoughts about it? Maybe you can talk about it.
Yeah, so the question was about doing this directly in video. I'm kind of agnostic to that. So for me, the challenge is if we can take novel input and produce semantically rich gesture. So novel input, I mean novel audio, say, novel audio and text. And if we can produce semantically rich gesture for that, I'm excited, right? And so that's the goal that I want to see. And I don't mind if that's sort of direct to video, if that's going through a 3D system. Yeah. And there's an even deeper challenge, right? Like we will say things, like I could say something like, oh, I met this guy the other day, and I'm giving you an indication of the person's height. That's not in the verbal channel at all, right? So we will generate, part of the information that we generate non-verbally is not in the verbal channel at all, right? And so we need to fundamentally rethink all these architectures in order to represent that, right? So if speech and text are our only input, we're never going to get that, right? So we need to add these other sort of kinds of input into these systems. And I haven't seen work tackling that yet, but
Equal speech.
Just a follow-up question for the internet scale of data that we are not using to generate the data set. Do you think that not having a very good pose estimator of a person, which can get the intricacies of the gesture movement, is limiting somewhere else to get the data generated? And if not, what's the problem?
So certainly better and easier to use pose estimators would be helpful. Again, that's not exactly what I work on, right? So I'm not necessarily with the state of the art, but they're getting a lot better. I'm not convinced that they're quite at the level of mocap yet, so better quality would be better. Really good quality hand tracking. So there's been good progress on this, but really good quality hand tracking from video source is still challenging. Yeah, so it would be helpful. Yeah.
My mind is that sign language can be a special case of gesture generation that has a one-to-one matching between the language and audio.
Yep.
You in this field, so I'm just wondering if that data of sign language can be adapted or have some relation with the
Yeah, so there's something called Kendon's continuum, and basically it lays out these different forms of kind of hand movement that we do. And at the far end is sign language. And because sign language is a formal language, so it has a grammar, it has gestures that have very well-defined meaning. So it's quite different to a co-verbal gesture, right? Where you kind of lose all of those properties of having a really crisp definition. It's not clear to me how much solutions to one transfer over to the other. Because sign language, generally the problem is you're going from text to sign language. And so you don't have this audio correspondence issue, which you have with co-verbal gesture. So it may be possible, but they're also quite distinct areas. Yeah, it's a good question. Okay. Any last? Yes. Yeah. Mhm. I'm not sorry, which? Yes. Uh-huh. Yeah. So the first question was about mesh penetration, and this is something that I think learning systems will probably be very helpful for, right? Because as long as your mesh matches the proportions of the actual person, you can generate something that is within the distribution that shouldn't have interpenetrations, right? So you probably can get this out of learning systems. The second question about having richer data sets of semantics, will this help solve the problem? Yeah, absolutely. Absolutely. One of the issues is that gesture has a real long tail problem. So I have a colleague that has this Megyn Kelly example, who's an American TV anchor, but she's explaining the Democrats and the Republican Party, and she has like the Democrats are here, and then the Republicans are here, and then there's this sort of, and she's doing this really complex visual explanation using metaphor of what's going on. That's something that she probably has done once, right? And so this is a challenge in how you kind of deal with the sort of really low frequency occurrences of these gestures. But I think, yeah, more semantically rich gesture will help. Yeah, thank you.
Okay, so we're going to take a break, and we're going to start again at
Mute. Okay. All right, now we're all set, shuffling. Okay, so I want to start my talk with this question. Why are you interested in 3D human motion? I'm not really asking the audience here. This was actually a question somebody asked me when I just started doing 3D human motion synthesis as a grad student. The person who asked me was Jessica Hudgens. I don't know if you know her. She's a really well-established, famous person when I started working in this field. And she asked me when we first met at SIGGRAPH, and I was surprised by this question. I didn't know how to answer. And eventually I uttered something completely unintelligent, and I felt really bad about that for many years after that. But later I thought about this, sure, it's not the most profound answer, but at least this is an honest answer, right? It's an honest answer that actually motivated me for many years. So 20 years passed by, I have a better answer for Jessica now. And of course, the things that we're doing, not just for video games anymore, but still a lot of things we're doing are really motivated by real world problems. And that's really important for me, for my lab as well. So of course, we're still very much interested in this core agenda of computer graphics, right? We want to be able to create digital content that's realistic, and human movement is really important part of it. We're very interested in robotics, right? Because knowing how human moves can help robot to move more like us or interact with us better. We're also very interested in healthcare, and I'm not just downloading some random images from the internet. We're actually doing this. We're building exoskeleton from our lab, and a lot of things we learn in human motion turn out to be super crucial for a better exoskeleton design. And we also work with partners to apply this human motion synthesis to industrial design for ergonomics, for logistics center workflow design. So half of my lab is interested in this little character here. Our goal, so this little character knows how to move by itself, but it doesn't really have a brain. So in fact, it always depends on this human brain to give this little character a command. So you can imagine that this little character has its body that lives in the virtual world, but its brain lives in the physical world. And the other half of my lab is doing exactly the opposite. We build a bot, and we call this character animation, right? The other half of my lab is doing exactly the opposite. We build a physical body, and that physical body is driven by a virtual brain, and we call that robotics. So for this virtual brain, in the past, we always believe it's some kind of planning, right? High-level planning. Nowadays, we call it AI. But I think a better, more precise term for that would be embodied intelligence. And this is actually the notion that I want to emphasize today. This is where I see a lot of new challenges and new opportunities for character animation or for human motion synthesis. And so our idea is that we want to be able to endow this character, not just ability to move, but ability to see, to hear, to speak, to touch, and then use its own observation of the world and reasoning to make intelligent decisions. So this requires a lot of things to be researched, to rethink a lot of a process that we've been doing in the past. First of all, we need to think about how we capture human motion, human movements for embodied intelligence, and we also need to think about how we train new model, large multimodal models for human motion. We also need to think about how we can adapt those pre-trained models for embodied applications. So these are sort of three buckets of research directions that we're very interested in our lab. But today I'm going to just focus on embodied data. So before we collect data, I think that people have a different philosophy about data collection. For us, it's always the last resort. We want to be able to build models to do things we want to do. And we look at Michael Block, do you have a data set already? And if he does, then we'll just use it, right? But oftentimes, so the first thing before we think about motion capture, something new, we need to think about what kind of models we want to build. And for us, you know, in the past in computer graphics, we always think about the high-level commands will come from user or some kind of a you know, procedure that generate these commands. And the output of a models usually is the trajectory of a poses. Recently, people start to think about trajectory generation or pose generation as a distribution, as learning a distribution. So this allows us to build those generative models where you can start from a random seed and then ask the model to just generate those infinitely long human motion sequences that are random, but they're learned from a real human distribution. But the most interesting to us, is that we can condition this motion model on pretty much anything nowadays. You can condition it on what the person sees, what the character sees, what the character hears, what the character remembers. And if you also have label data, like paired label data, medical data, then you can really use this model to do something in the healthcare domain, right? If you have biomarkers, you have some kind of anatomical properties, and you can use that as your input and predict the outcome of maybe you know, outcome of an intervention, a medical intervention. So, okay, so that's kind of things we want to build, right? We want a model that can have multimodality observations paired with the actions. So we need data that give us that. So you go back to where we collect data today. The gold standard of data, 3D human data collection, is still optical-based motion capture systems. And this is designed to collect really just the actions, but not observations, right? We know what a person is doing, but we don't know why the person is doing these things, these actions. So in other words, we know how to record proprioceptions, but we don't know how to record other modalities of perceptions like vision or tactile sensing. So that's the first issue we need to address when we talk about data collection today. Now, other things that we care about, well, when you are working in biomechanics, healthcare related applications or robotics, oftentimes you care not just the poses, not just this kinematic information, but rather the dynamic information that give rise to this kinematic information that you can observe. So for example, you care about muscle activation, joint movements, joint torques, or contact forces. So we need to be able to capture both the kinematic and dynamic information if we believe that what we're doing one day can be used for healthcare that can actually, you know, enable a lot of new technologies in other domains. So kinematic, going back to where we collect data today, we only collect kinematic data, and that's not enough. We need to figure out a way to collect both kinematic and dynamic data. And then finally, the last requirement is actually something you probably know already. It needs to be large. It needs to be large in terms of a quantity. It needs to be large in terms of a diversity. And we want to be able to have a motion capture system that can collect data in the wild, around the clock, and at the same time maintain accuracy, high diversity, multimodalities, with both kinematics and dynamics. That's kind of the data set we need for human motion, at least in our view. So how do we get there? I propose 3 steps, and this is exactly what's shown here. The first step is that we need to be able to acquire contextual motion, not just the motion of the subject itself, but also the world around the subject. Sadly, we don't really have a good way to collect contextual motion data, but our goal is, you know, we should stop there, right? We should think about new way of motion capture system, invent a new motion capture system that can achieve this goal. So that's exactly what this project is about. We want to capture human movements in a highly contextual environment, along with the egocentric observation of the world. So for example, if you're picking up something underneath or behind the toilet, and in this very, very cluttered environment, your body is doing something completely non-trivial, right? To be able to reach where it is. And at the same time, we want to be able to get the paired egocentric view of what you're doing. Again, we want to be able to answer the question of why, not just what. Why are you doing this? Because this is the world that you observe. And how do we do that? Well, you know, Vicom, Motion Capture, or other companies, doesn't matter, will give you very high detail, accurate 3D human motion if the space is clean. But if you want to build a or bathroom in your lab, it's going to be expensive. And also it's going to be, generates a lot of occlusion that's very hard to fix later. So our idea is to combine motion capture with virtual reality. So the subject is wearing the VR goggle, and a very contextual virtual scene is streaming to the goggle to create an illusion for the subject to perform task. And then we will ask the subject to do something that engage the environment. For example, picking up a pencil underneath this podium, that kind of motion. And this is a one session of a contextual motion capture. You can see that we're capturing this the subject in this collision-free environment, which is great because then we get very accurate 3D motion. But at the same time, this is what the person is seeing, and that actually trick the person to believe he is in this environment and try to unplug something behind the chair. Okay, so we collect 10 hours of the data. We call this data set circle. Another really good things about virtual scenes that you can be very diverse, right? It's really cheap to just create all different kind of virtual scenes. All right, so this is a project we published last year at CVPR. What about physical contacts with the environment? For the first circle data set, we didn't have any physical contacts with the objects or the furniture in the room. So this is the next thing we want to do. But this is more tailored for robotics, so I'm going to be a little bit quick on this project. So our goal is to create a new motion capture devices so that people can go out, collect hand motions along with the object motions in the wild, and then later on we use that to teach robots how to do the same thing. So how do you collect hand motion, dexterous manipulation? The key here is that it's not just about the hand, it's the hands and the objects, and they have to be paired. They have to be in correspondence. So Michael Block indeed has a data set that collects the data in the lab settings, right? It's a really nice data set, has a lot of detail, hand motion, very accurate, high quality data. Except for it's very difficult to do the same thing in the wild because they use optical mocap systems. And you can also try to use VR headset. VR headset comes with this hand tracking capability. The problem is still the occlusion and also the because it's vision based. So problem is occlusion and also the limited field of view. So we built a complete different. We took a different approach and built this new motion capture system. We call it dexterity capture, DexCap. So DexCap is something that you can just carry with you and go out. And it contains the gloss, which is IMU based. You can get a really good detailed finger motion, but those finger motions are not grounded in a particular coordinate frames. So we need to have additional SLAM plus IMU cameras that will give you the 6D pose of each of your wrists. And finally, we have these RGBD cameras that you wear around your chest, which will have two purposes. The first is to capture the world, the environment. And the second thing is to help with the localization, calibration. Okay, so before we started, we need to first calibrate the system. Is it on now? Can you hear me better?
They do.
All right. And then we can start recording the data. I'm just going to continue because I might run out of time. All right, so just quick test. If we just use SLAM and IMU, this is how accurate our wrist localization could be. So my students moving around, and you can see that after 30 seconds or so, he can come back to exactly where he starts. So the drift issue is not there. But if you just use IMU without SLAM capability in your cameras, then you can see this kind of a drift starts happening very quickly. And then at the end, this data is just not useful for long horizon capture. All right, so this is what DexCap in action. You can see that at the beginning, you just move around and to calibrate all three cameras. Once they are calibrated, they're in one single chest frame, coordinate frames, and you can start just, just take out those SLAM cameras from the cradle, put it in your arms, and put it on your wrist, and start collecting data. And that's it. You go out, collect tons of the data in a very quick, convenient ways, and then we want to train a policy. So, can you hear now better? Oh, okay. There's no difference for me. All right, now I don't need to show. Is it better? Okay. So how do we build a policy here? It's actually very easy. And then our whole idea is that if you have a good data in distribution data, you don't need a fancy policy, but you do have to do retargeting because we collect data from human hands. And there is a difference between human hands and the Leap hand, which is the multi-finger robot hand we use. First of all, Leap hand only has 4 fingers, and it's a lot bigger than human's hands, right? So we need to be able to retarget at the Cartesian level. Cartesian meaning XYZ, right? Like if you just directly map a joint angle, it's not going to work. So we map the fingertips. And that's super simple. If you ask anyone from computer graphics, like Michael, he would say, well, that was done in the 80s or 90s, right? So there's not much, fancy stuff we did for retargeting. But after you're retargeting both the observation and the action space, then you just train a policy, diffusion policy using behavior cloning. So nothing fancy at all. And when you're done with the training of your policy, you just go to the robots, give your robots this policy, and the robot will start performing something 0 shot. That's actually pretty reasonable. I mean, considering this is how little thing we did in policy training. So the idea is that if you get good data, human data, then things will work pretty well. And they also have the ability to generalize to different initial states and different initial conditions. All right, so I'm gonna skip that. This is robot slow. I was considered to fast forward that, but I know that most people don't like to see fast forward. At least want to see the actual speed once. And now we can fast forward the rest. So we can collect data in the wild. That's the main purpose. And now Chan is walking in our basements at Stanford Gates Hall and then collect all different kind of data. So here what he wants to collect is 2 hands by manual manipulation and putting packing the object into a box. And we collect 6 different kind of objects. And our goal is to be able to generalize this packing skills to new unseen objects, and it actually worked pretty well. Again, almost 0 shot transfer. Okay. So we're also thinking about long horizon data set. Long horizon task. Here, Chan is demonstrating how you prepare tea, making tea. So first you have to twist open the bottle, which itself is a really challenging robotics task. And then you want to, get some tea leaves out of the bottle using the tweezer. And now we do the same thing on the robot. So for this particular demonstration, we did use a little bit of teleoperation to help because this twist open is really difficult without haptics. And that's not a kind of new thing that we're working on as well. How do we actually include haptic as one of the multimodal observations that we can collect from the real world? All right, so this work is collaborated with Feifei, and the published at RSS. We'll have a presentation in 2 weeks in Netherlands. And you can check on our website, and you can find the paper, the code, and very soon we will have a video teaching you how you put together your own DexCap. It's not that difficult, as you can see from the demo. Okay, so that's step number 1. Step number 2, how do we get dynamics data? Because most of the motion captures, even the DexCap and a lot of things that I talk about up to this point, we only collect kinematic data, just the poses. I want to know what is the joint moments, what are the joint torques that give rise to those poses I see. Sadly, we don't have a way to collect dynamic data, but hundreds of biomechanics labs in the world do. So what they have that we don't is this thing called force plates, right? So they are collecting very accurate contact forces, ground reaction forces at the same time together with a Vicon system. The problem with the biomechanics data is that they don't share data. They work for that specific experiment, so they don't collect a lot of data. That's the first thing. And also their data collections are very heterogeneous. Like some data has IMU, some data has only upper body. So it's just very difficult to make them machine learning ready. And that might be the reason they don't feel like they need to share the data. So we introduced a web-based tool called App Biomechanics to fix this problem. So it's really just a simple data, motion capture data processing tools, if you look from the outside. And our goal is to make this tool available to everybody so you can use it, and you can, you put your raw motion capture data there, and you get back a scaled digital twin, a skeleton that fits both kinematically and dynamically. Because when you give us motion capture together with a force plate, we can try to, come up with the motion that fits both the equation of motion as well as the markers and the forces that you collect. Okay, so how does App Biomechanics help in terms of data sharing? So if you see this is the kind of landscape we're looking at. We have some public data set for human motion, but there's a lot of private data set. They're really good data, but they're just not shared. So App Biomechanics expedite the data collection cycle so people can collect, that's the first step. We want people collect more data more easily and more cheaply. And App Biomechanics process the entire post-processing pipeline, which means that we can make sure that the final data sets are harmonized and machine learning ready. And how do we help in promote data sharing? Well, we let people use App Biomechanics free of charge in exchange for their consent to donate the data. And with that, we believe that we can build this unprecedentedly large human motion data set by harnessing and aggregating the effort from the entire community. So I'm just gonna be super quick on that. This is, how much time do I have? I started exactly. Okay, all right, 15 minutes. I think I can do this. All right, so I think most of the people who are in this domain kind of just probably is wondering right now, why do we need motion capture processing? We have the tools for that already, right? Those companies where sell your motion capture system comes with those software. Why do we have to solve this problem again? This is actually a misconception, because all those tools that you're using, if you really try that, they're not really automatic. There's just a lot of corner cases that will take days for especially large amount of data you want to process. Another, reason that we need to, innovate again on this old problem is because we want dynamic information, right? So most of the software that you can use today stop at the kinematics level. So they don't give you torques, they don't give you muscle activation, and we want that. So one way to do this, is just the traditional way you solve it. It's just giant, you solve this problem step by step. The problem with that, you would generate a lot of arrows. Arrows going to be propagated to the subsequent stages, and at the end, accumulated. You can't do anything about that. It's too late. So the right way to do it, we all know, is to solve a giant joint optimization problem that solves for pose, marker location, bone scaling, body mass, joint torque, contact forces, muscle force, all of that you can imagine in one optimization. And of course, the problem is you cannot solve it because it's non-convex, it's really challenging, and the initial guess, becomes the most important thing to tackle the local minimum problems. So what we want to do is to essentially find a set of poses post trajectory that satisfy this equation exactly. And this is for those who are not familiar with physics, this is really just F equals ma, okay, in the Lagrangian formulation. Now, the interesting thing is that in order to fix this, to fit this equation, we have two sources of ground truth. We have one source coming from motion capture system, they give you markers, and we have another ground truth that's coming from the force plate. Which one do you trust more? Because none of them will by itself will just satisfy this equation right there. So if you plot out the center of mass trajectory using the, so let's just assume this is ground truth. The black curve is ground truth. If you use the marker position to compute the joint angles and calculate the center of mass, you get this green curve here. If you trust your ground force place, you get this purple curve here. And oftentimes people start with the marker position because it looks closer to the ground truth. But if you look in the acceleration domain, you realize that the ground truth from the marker positions are is much noisier, right? Because you see that little bit of noise in the position when you calculate acceleration, they give you huge spikes. On the other hand, this curve coming from the force place already satisfy physics, so you get very smooth acceleration. So we propose we shouldn't start with the marker position. You shouldn't start with the traditional what motion capture system gives you. You start with force place. Make sure that your initial guess already satisfy physics. This still require you to solve a passive dynamic system expressed as a linear system. You can solve that, and then use that as the initial to fit the markers later. That's a lot easier. Anyways, those are sort of little details that we did. And at the end, we were able to create a qualitative, high quality motion that's together with both kinematic and dynamic information, and also high diverse and large quantity. So we have 70 hours of data that has both kinematics and dynamics in there. Here's an example to show that once you get joint moments, you have ground reaction forces, you can do another inverse dynamics to get your muscle forces with some assumptions in there. Okay, so we released app biomechanics. We'll put it online, and it's been there for a year. This is the old numbers, but we got 23 university, most biomechanicists joined this during this effort, and we collected tons of data. We did not collect a frame of the data ourselves because we don't have a force place, but they do. So why don't we just get their help by giving them something first? All right, so if you have kinematic motion capture data, just give it a try. It's really simple. We make it extremely easy and streamlined. You go to the website, you drop your motion capture data, you wait for a while, maybe a few minutes, and you will get your digital twin back along with the kinematics and dynamics information. Now, why do we want to collect the data? Let me be quick on this too. Eventually, what we want is to be able to predict dynamics from kinematics, right? Collecting data we see as just the initial seed data set, right? You need to start with something that's ground truth. But after that, you have enough of that, you train a model, and then you don't need the data anymore. That's the goal. So this is what app biomechanics can give us. We have a joint trajectory paired with a joint torque and the external forces. Essentially, we want to get joint moments. That's what a lot of medical healthcare related applications care about, ergonomics as well. But it turned out it's actually easier to predict the external forces instead of a joint torque because it's a lower dimension, and also there's a directly labeled, right? We measure that. And once you get the external forces from physics, we know how to get back to the joint torque, right? So the last step, going from external force to joint torque, can be solved analytically. Okay, so now I'm just going to put some label color there. So everything that you can get from joint trajectory is shown in green. Everything that's related to external forces like ground reaction forces is in this teal color, and the joint torque is in purple. All right, so if you stare at this equation long enough, there are multiple equations here. That it's not, so you see like matrix and vector, they're multivariate. When you look at that, you realize this Jacobian, right, J there, is problematic because oftentimes it's low rank because you have multiple contact points. If it's just one single contact point, you're all good. You can just solve that analytically. But you have multiple contacts, then you're in this low rank scenario, which manifests to this one-to-many mapping that you have to learn. And to learn one-to mapping is hard, but we know that generative model is a good candidate type of a model to use. So we try to do this with diffusion model. And I'm sure most of you know what diffusion model is. So I'm not going to talk about that, the details. But the idea is that we are going to pretend this is an image. Okay, so the sequence of joint angles and joint angle velocity, which you can get from kinematic data, along with the external forces you get from app biomechanics. That's my image. And I'm trying to learn a diffusion model that can generate this image from noise, okay? And when I really use it, the way I use it as an in an in-painting way, right? So oftentimes I have the joint angle velocity because that's what a mocap system can give me, but I don't have external forces. So I force the learned diffusion model to give me that by trying to come up with a paired external forces. So that's it. That's how we predict external forces. And then here's some qualitative results. You can see that even with this kind of pathological gate, we can actually predict the ground reaction forces pretty well. So what you're seeing is ground reaction force measured is red, predicted one is in green. Okay, so another really interesting thing to do is to predict what kind of how the kinematics changes affects dynamics. Okay, so what we did is that we make the trunk sway 2 times more from the original data. So original data is in gray, and we just created more trunk sway in the motion in the just in poses, and then turn out that we could use our generative model, diffusion model, to predict joint moments after this change, and then we compare that with experiment results, and they're actually quite close to each other. So this is a really preliminary. I have not published anything yet. Anything you want to publish in biomechanics needs a lot more testing, and not saying that CVPR you don't, but just you do have to go through a lot more experimental and comparison before you can publish anything there. But anyways, that's sort of the second step that we're our plan for the second step. The last step is about scaling up the learning process. So we need a lot more data. That means we need to collect data in the wild around the clock, right? So there are many different approaches. One approach I'm going to talk about today is just use cheap wearable sensors, IMUs specifically. So we want to build an IMU motion capture system that you can wear them and go out and in the wild perform mountain biking, skiing, or simply playing with your kids and collect the data for the community. So we did that. 2 years ago, we built this IMU system that requires only 6 IMUs, and then we use this machine learning tools to predict or to reconstruct the full body motion. This year at CVPR, we actually did something more. We created a new techniques that allow you to reconstruct full body motion from arbitrary numbers of IMUs, putting at the different parts of the body. So the way we do that is diffusion model again. It's almost the same trick. We at the beginning think about this as the image now. Every row here is one reading of the IMUs over time. And usually when you wear the full set of IMU, you need to wear at least 16 or so. So we have 16 rows, more than 16 because each row is a vector. But during training, we have that kind of data. You have this data set of a full set of IMU, and then you train the diffusion model. During inference time, maybe for this particular experiment, you only have 3 IMUs available, and you put it on the knee, on the elbows, on the hip, and I mean it's your choice. But whatever you do is going to be some of you just provide that signals to your diffusion model, and diffusion model through this in-painting techniques can give you the rest of the rows, which will give you the full 16 IMUs, and from there you can reconstruct really good human motion. Okay, so quick demo on that. So here we have Tom walking with the 6 IMUs, and then we can reconstruct the motion in real time. And then now he removed 2 IMUs, he only has 4 IMUs, but without retraining the model, you can just directly during inference time get your model, your motion. Okay, so since I don't have a lot of time, I'm going to skip this new work. We collaborated with Meta. You will see this work in details in the egocentric workshop later today. I think it's also in this building. Now, I know that data collection or collecting data in the wild using IMU is just one way. There's another really good approach a lot of you guys are working on, right? Using the 2D data. This is where computer vision could be super useful. We just begin to look into this field, and I'm very happy to collaborate with anyone who's interested in collecting collecting for human kinematic motion using existing videos. Okay, so in summary, this is how I see kind of steps that we need to take in order to get our large enough of the embodied data set for embodied intelligence, both for both computer graphics and computer vision as well as robotics. I'm happy to take any questions.
So you described the method to extract the talks using data. And I wonder what would be the pros and cons of this approach compared to using the other physics simulation, like
RL.
computation.
Yeah, so a very good question. So another approach to get dynamics information from kinematics is to just use RL. We can just train an RL policy to mimic the kinematic motion. And because RL has to learn that through physics engine, physics simulation, so you will end up getting your ground reaction forces and joint torques. I believe that until I actually see the joint torques you get and the contact forces you get, that's when I think we really need a human to give us this demonstration, because the data the RL, I don't know if you ever look at the contact forces you have, they are not anywhere close to what the actual forces human generate. So RL with just kinematic supervision, it would not give you the same kind of a joint moments there, because there's many ways that you can achieve that same kinematic motion. And RL always cheats, always figure out a way that you don't want. So that's why we're not considering using RL. Question?
Yeah, you said that one way to get context is to create a virtual scene and put the virtual reality headset on the individual not being recorded. Then you mentioned there's still a challenge if you want to have record interaction with an object. What do you do? You want to put them down or handle an object in the virtual scene?
Yeah, so the first project is actually not addressing the contact, right? The virtual scene here, we have a very specific goal, which is just reaching in a very cluttered environment, no touching. And that's why virtual reality works well, right? Yeah, so that, so if we really want to, dealing with the contacts, right now we have multiple approaches, but it all kind of involves physically collecting data in the real world. So the DEXCAP is one way to do it. We have another, data collection process that try to do the full body manipulation with objects. You will see that in the egocentric workshop in the afternoon. But they're just, we don't have a good way to do it. We still use motion capture and try to do it as a good job as we can.
Yeah, thank you very much for interesting presentation. I have a curiosity regarding the last method that you are presenting at CVPR, where you can construct the whole walls and dynamics given only few landmarks. You show that it works real time, no? So I'm curious because in many of these systems, you need to define many denoising steps, or maybe the denoiser is based on transformer that has several parameters. So did you do any special trick or treatment to make it real time? Or you found that only very few iterations of the denoising was useful, or
yes,
how did you make it?
Yeah, so let me go back to that. So to make it this real time, I skip this slide. You skip a lot of steps. You don't do 1,000 steps, and you don't need to actually. And we use DDIM for that. And B, we actually only predict that. So most of the histories are given, right? So actually the part that you need diffusion policy is really just that one last frame at the end. Question in the back? Do I believe what will replace this? 3D pose estimation from vision. Is that what you mean? Yeah, because we are doing 3D pose estimation too, just different way. Do I believe this will replace motion capture? I hope it will. I really do. I think that will really, change the game. We can use the cameras, whether it's egocentric or third person perspective. I think right now it's not there yet. And we are getting greedier too, because we don't want to, if you just talk about one person without the contextual information, doing something kind of just normal, like walking, running, jumping, locomotion, I think the vision is there already. But we want more, right? Every time we want more, we kind of have to go back to the best technology we have. And hopefully we can use that to get us a really high quality data set. And that can serve as a, something that we can use to bootstrap the field.
Capture my camera is for training. There are other situations with camera. Think of skydive, climbing up mountains, or water sports. We think of sensor based more capital. I would be in the future it's so situation.
That's why we build the IMU base, right? So the whole idea is that it's portable, it's egocentric. You can carry this with you. You don't need a third person cameraman following you around, right? So there's definitely a lot of good properties. But then I guess it's just sort of, we're very flexible. We're not saying that it has to be inertial based, right? Egocentric is something we believe because it's convenient, but it could be vision based egocentric. And also a combination of that, which it was actually that project we did and I skipped. Yeah, so the camera is on the wrist.
Yeah, take the last question.
Okay, I'll take why don't you pick?
Hi, thank you for a nice talk. Thank you for a nice talk.
I can't hear you, that's fine.
I'm also interested in motion capture from sparse sensor input like smart alternative views and so on. And we say that scaling of human mocap data is important, but I'm curious about the use cases of the mocap data. Maybe like using in robotics, like hand to hand, like to copy targeting to humans, noise can be an example. But I'm curious about the other examples and other use cases that you're seeing.
Yeah, so there are a lot of use cases. I started with that, at the beginning. I don't think I can get there in time. So we're looking to robotics for sure, like you mentioned, right? Human demonstration, because nowadays humanoid is a real thing. At least, who knows how long it will stick this time, but people believe in humanoids again. So that's exciting. And then, when you talk about humanoids, human motion becomes, a first-class citizen again. Now, that's just one thing, though. We're also very interested in healthcare. We're building we're designing a exoskeleton that can detect the fall before it happens and prevent the fall, actuated just in time. And really, the most important thing is to sense the person. Actuation is not as hard as I thought. Turn out sensing the human, what human is doing and what human wants to do, so that we can intervene in a way that doesn't override humans' autonomy is such a fun problem to work with. Sorry, he said that was the last one. We can talk about later.
Yeah, so let's thank Karen.
Thank you.
Unmute. Good. So I will present the work we have done in my group on human motion synthesis. Does it work? Yeah, okay. So I'm from the vision community, right? So when I present like works on synthesizing human motions to the vision like groups or audience, they often ask me, why do you want to work on that? Do you want to work on computer games or character animation or other applications, for example, virtual characters in metaverse? So I think those are all very important applications. But the reason actually we start to work on synthesizing human motions is motivated by computer vision tasks. So I want to bring realistic virtual humans into real world simulators. So if you think about like these days when people try to train, for example, autonomous cars, right? They often build simulators. And if you look at these simulators, if we want these autonomous cars to be able to really detect different human behaviors, they need to see diverse and like realistic human behaviors in their simulator, right? So what we want to do is to bring this realistic human behaviors into the simulator. Later, we can train better perception models. So if this is the goal, right? If this is really application you have in mind, and then the question you have is, at least I have is, what kind of motion model I need for such application? So I would argue, I think the motion model we need, first, it should be generative model, where we can really synthesize and generate lots of data, right? Different data. It should really be generative model. It should be efficient. We want to generate lots of data for training perception models, right? It also should be diverse. So we should have a model which can really model diverse human behaviors, and later we can replicate such behaviors in the real world simulators. And also controllable, right? So we might know from external knowledge, right? Certain type of human behaviors cannot be detected or predicted by perception models. And then how can we really control our generative model to generate certain type of behaviors, right? So I think those are the kind of goal. And having this in mind, in my group, we have been working on this topic for the last maybe 3 or 4 years. And today I want to talk about 3 very recent work. So the first one is DNO, diffusion noise can serve as a universal motion prior. And here it's a very simple algorithm, but our goal is to see whether we can leverage diffusion models as a prior that can be used for many different motion control or editing tasks. The second work is called DART. So it's a very new work. We haven't put online yet, but we will put it soon. But we finished this project. It's a diffusion-based autoregressive motion model for real-time text-driven motion control. So here, the goal is really to have a real-time or online motion generation model that can be controlled by text. And the last one is EgoGen. So egocentric synthetic data generator, and will be presented also this year at CVPR's oral on Thursday. And I'm very excited about this work because, as I mentioned, right, the reason we are doing motion synthesis is we really want to bring these realistic human behaviors into simulators, right? Then later to train better perception model. And this work is kind of one of the first work we have proved that we can do that. By building a better human motion model, we can actually improve certain type of, or we can really help certain type of perception models. Okay, let's start with the first one, DNO. So this is a joint work with people from Google and Berkeley and Vistec. So I think this audience, we all know the recent 2 or 3 years, there are really exciting progress for text-driven motion synthesis, right? And I want to talk a little bit about what are the ways to control the human motion, to control this text-driven human motion. I think the first 2 kind of ways are autoregressive motion token, right? For example, Motion GPT, and also diffusion-based model, for example, classifier free guidance, MDM, and MLD, like this line of work. And I think the advantage of this line of work, when you consider about motion control, is they have good quality because you really have the paired motion data and control data, which you can train, you can learn this conditional distribution, right? And it's also the problem. You need really paired data for training such control models, right? And then there also works like on loss guidance, where you don't really need lots of pair data. And it's like this loss can be like this guidance, or this control signal can be any differentiable like objectives, right? And then you basically try to inject this objective in the diffusion process, and then you can achieve certain kind of spatial control. And the example work like a GMD or trace and pace and or FaceDiff, right? So they all use this type of way of doing motion control. And the CVPR work, this DNO, I think it's kind of in this category, but it's not, instead of really introduce a loss guidance, what we do is very simple. We basically try to optimize the diffusion noise based on certain objective. So these two ways are more flexible and works with, as I mentioned, differentiable loss guidance. So how we manage that? So our work is actually inspired by this work, end-to-end diffusion latent optimization, improved classifier guidance. So what they did, the core idea of this work is to backpropagate the gradient from certain loss guidance through the entire denoising chain, right? But it's not easy, for example, because of a memory limit. And what they did is they use an invertible model to avoid keeping the activations in the memory and to enable the output optimization. And the problem here in this work is it still needs lots of memory, and it keeps 4 times the memory per step to use this additive inversion, another work, and it doesn't work with standard optimizer, right? And can we do something simpler? So that was our motivation. Can we get rid of this invertible modular? Can we just directly optimize the latent noise? And actually, what we showed in this work is in motion domain, right? We can really do that. It's very simple. So the core idea is to backpropagate the gradient from the diffusion process and then optimize the noise vector based on some user-provide loss functions criteria in the motion space. So just an illustration, right? We start from some noise, random noise. We go through this ODE solver. We get the motion. And then what we do is we define an objective in the motion space. For example, the person should avoid some collision, or the person should reach some certain point. And then we backpropagate the gradient through this ODE solvers to update the diffusion noise, right? We can do that. There are 2 things. The first thing is motion, right? It's not like the image. Motion here is a much like a kind of the data is smaller, right? It's your motion representation is not like the whole image, right? So we can put it in the memory. The second thing is we use this DDIM solver, which we only kind of do 10-step diffusion steps, right? So we can do that. This is a very simple algorithms, and this is an illustration, right? So this is a diffusion noise, so latent space, and this is a motion space. And for example, this is a target motion. And what we did is basically to define some criteria function, some loss function in the motion space. And then we backpropagate this gradient through this ODE solver, and then we update the diffusion noise, such that once this noise is updated, the generated motion kind of follows the criteria, right? That's the idea, very simple. And in this work, we show this can be used for motion editing, motion in between, motion denoising, motion blending, and other tasks. So in the next, I will show you some like result. So for example, this is motion editing, so to avoid the obstacles. And this is an input, just motion generated from text, for example, walking and raise your hand. And if we put some obstacles on the way, and then you can see there are humans in collision. And if you basically, in your criteria or in your loss function, you try to push the human away from these obstacles, right, by the SDF or something like that, you can see the optimized noise, latent noise can generate this type of motion that can really avoid these obstacles. And there is another example. So basically, this is added PAVEX location. So you see this is the input, and all this yellow, blue dots are the PAVEX locations at certain point. And what we want to do is, or what we did is basically to drag these PAVEX locations to the yellow dot, right? And you can see this is optimized motion. So basically we optimize the diffusion noise, and then it can generate this motion, can kind of fulfill this type of guidance. And there is another example you can, so this is basically another task, motion in between. So the target is to generate a motion that can filling in the motion, right? So we have the starting frame, we have the ending frame, and then you can define a criteria function for that. And you can see the optimized diffusion noise can generate such motion to really like kind of filling in between. And this is another example. And I should have more example. No, okay. And the last task I want to show is motion denoising. So the input is this noise, very noisy motion. And you can see this noisy motion like input here, right? This orange dot. And by optimize this diffusion noise, you can actually generate the motions that are much smoother, right? From this noisy motion. Okay, so for more results and quantity evaluation, you can check the paper. And I want to summarize here. I think DNO is a very simple algorithm, but it's a unified framework. And we can use, it tells us like we can use diffusion-based motion model as a general motion prior for many different tasks. But there are also limitations. For example, this optimization happens in the learned motion space, which means if you don't really see certain type of motion, sometimes some motion is just too difficult to get given the limited training data, right? So it's not like 100% work. So it's really also, I mean, it's still limited by the training data. The second problem is slow, right? It's optimization based. So to get one result, we probably need to run, I don't know, a few hundred optimization steps. And for each optimization step, we need to backpropagate this gradient and also go through the DDM, like 10 steps. So it's not real time, it's slow. Okay, so that's all for the first work. Next, I want to present this START, a diffusion-based autoregressive motion model for real-time text-driven motion control. And the motivation is really like, basically, how can we achieve online real-time text-driven motion control, right? And the key idea is actually it's a latent diffusion-based autoregressive motion primitive model. And I mean, the following slides I added this morning, and I want to, I don't know, I think maybe it's interesting to discuss this. So I think when we model motion, right, it's really important to think about, it's interesting to think about temporal spectrum of human behavior, right? So the people, we all know, right, like poses, just static pose, it's a single frame, it's one, if you have a 30 frame per second, right, it's really just a single frame, but it tells you certain type of behaviors. Right? It's not always so kind of like you can always kind of link this pose to a semantic meaning, right? And the next level is motion primitive. So it's a short motion sequence, for example, less than 1 second. It includes some motion like dynamics. I mean, not dynamic, but it's really has the movement and it has richer semantic meaning, right? And then the next level, I mean, here I want to show you a motion primitive here. And the next level is action, right? It contains a few seconds. And if you think about recent, like many diffusion-based motion modeling, they actually works for a few hundred, 100 to 100 motion. I think it's probably around this level. It's really describe action, right? And then the next level, I think, is activities. So it's from the second to minutes. For example, like here I show example, but it's not playing, probably just images. And the next level is complex activities from minutes to longer, to hours, to days. For example, making a PhD hat, or render demo video, or decorate a room, learn to ski, cooking, right? So we have this full spectrum, temporal spectrum of human behavior. And what we have in terms, another thing we have to think about is the data, right? What we have, lots of data that we have is actually at this part. We have a lot of pose data from images, right? From 2D images, from 3D mocap, we have lots of such data. And but it's only give you certain semantic meaning. It doesn't have any like a human movement, right? It's missing this temporal domain, temporal aspect. And this action, right? Lots of people are working with, right? This 200 frames. If you think about actions, we have fewer data, much fewer data, right? Less data to train our model. It gives you more semantics, but it's much less data. And what I want to argue is when we think about text and motion and also training data, I think it might be interesting to really explore the motion primitives, which is just like a short motion terms, like less than 1 second. It gives you certain meaning of human activities, but it's not really long. And by doing this, you also kind of increase your data. And if you think about human motion, I think it's compositional. So if you try to model your human in this kind of like a temporal spectrum, and then you might be able to generate complex motions by the compositionality, if your model have the compositionality, right? And another thing I want to mention, right, before before the LLM, I don't think I ever dreamed about synthesis complex activities, for example, minutes or hours human activities. But now I think with LLM, right, it also gives us like this opportunity to kind of decompose the long human activities into short term. And if you really have a model that can really model human dynamics, like or human movement in short term, maybe there is a chance to really combine them and to synthesize complex long-term human activity. Anyway, so this is a new slide I added. And so basically what I want to say is I think it's an interesting direction to model short-term human motion. So that's exactly what we did. So we basically proposed this text-driven autoregressive motion primitive. So what is the motion primitive for us? So motion primitive for us in this work we given the 2 frames, history motion, as well as a text input, right? We want to actually have a model. Actually, here is a transformer architecture. We want to have a model that generates the future 8 frames, right? Less than 1 second, like 0.25 seconds. So that is our motion primitive for us. And given this motion primitive, right, we train this with AMA's data, with Babel data, I believe, and we can really learn a generative model, like a transformer model that can take the history 2 frames motion and the text input to generate the future like 10 frames. Right, so that's motion primitives, and we can run this in a recurrent way such that we can generate long-term motion. And by doing this, we can also kind of give the text or on the fly, right? So we can, while generating, we can give new text, and then this recurrent model, autoregressive model will take text into account and generate new motion. So here I just want to show you like a result, right? So this is a text prompt sequence. So first wave hand, and then you can see walk forward, turn left, sit down, stand up, hop on left leg, pace, in circle, dance, and stand. So these are, right, with right hand. So these are actually online. So basically this autoregressive motion takes this text input in an autoregressive way, and then you can generate this motion that produce most of the time smooth transitions. Yeah, I have, okay, I thought, so how many times, how much? 20 minutes, okay, I think I can do that. Okay, okay, thank you. Yeah, okay, thank you. So, okay, so now I tell you what we can do with this text-driven autoregressive motion primitives models. And now you might wonder what exactly this motion primitive model is, right? So this motion primitive model is basically the first, it has 2 parts. One is VAE, one is a diffusion, right? So the first thing we did is basically we learn a motion space. So we learn this like a motion primitive space using like a variational autoencoder. So basically now, instead of working with raw motion representation, for example, global trajectory, joint rotation, this type of things, we have a latent representation for this like a 0.25 seconds. So this is a latent space. And given this latent space, now we basically learn a diffusion model, right? Now, the diffusion model try to, during the denoising process, try to reconstruct this latent vector. And if you look at this diffusion model, right, this part is actually frozen, right, because it's pre-trained, this latent representation of human motion. And then for this diffusion model, it takes text input, it takes noising steps, and takes like a previous or like the initial 2 frames, and it actually generates the latent representation of the future 8 frames. And then this latent representation goes into the decoder again and give us the explicit human movement in the next 8 frames. So that's the architecture. Okay, so here is a comparison, right? So this is a floor MDM, a very nice work, will be presented this year at CVPR. So what they did is they predefine a sequence of text, and then they have an offline method which they can generate motions corresponding to the sequence of text with smooth transition, right? So this is their results. And what we have is actually, we did a comparison with them. We have an online method. And I would argue, based on our observation, I would argue our motion, like this Dart architecture, actually produce a bit better motion. I mean, yeah. But I think the FID is similar, but this motion is actually, our method is on real time, online, and it's has 281 frames per second, if I remember correctly. Okay, so the next thing I want to discuss about this Dart is how do we do motion control. So now we have a on real-time online text-driven motion model. How can we control this motion model with spatial information? So here we did 2 types of control. So one is optimization based, and the other one is RL based. So optimization based, I didn't put the math here. So if you are familiar with Humor, it's a very similar approach. So you do the rollout, you try to get the latent representations that fit your objective, right? So you can see, so this is a motion in between. So given the starting frames and ending frame, we try to get the optimized, we try to get the latent representation, this Z, that can generate smooth motion, natural motion that can reach the target, right? This is motion in between. And this is a human scene interaction. The first one is we give the text, walk, turn left, sit on the chair. And then we also give the target location, PEVX location. And you can see we can, by optimization, we can get the whole motion. And here is a walk upstairs. We also gave the scene SDF in the like a human scene collation based on the scene SDF. And you can see it's actually can generate I mean, not super natural, but reasonable motion, I would say. Okay, but one thing is this optimization-based control is not real time, right? It's like Humor, you do this optimization, it's not real time, but you can get the latent variable. And how do we do real-time control? And here in this work, we showed we can do real-time control using this latent space learned by Dart using RL. So we can't really do free text now. I think learning a policy that works for all kinds of texts itself is a very challenging task. So here, what we can do is we can have, like, for example, run, hop on the left leg, hop on the right leg, or walk. So given this type of text and given the target location, and then we can do kind of a real-time control with this Dart, with RL algorithm. Okay. So that's all for the second work. And next, I will present this EgoGen, an egocentric synthetic data generator. As I mentioned in the very beginning, right, the motivation for us to work on human motion synthesis is actually to improve certain perception models. And in this work, we show actually by designing a human generation model, motion generation model, and combined with graphics assets, we can actually synthesize lots of training data for egocentric tasks, and we can improve certain egocentric perception, like a task, the performance. Yeah, we can do that. Okay, so this will be an oral presentation on Thursday, and this is a collaboration with Microsoft. So with EgoGAN, right? So this is the data we generated from EgoGAN, and you can see we can have all kinds of ground truth data for vision tasks. For example, depth image, normal map, optical flow, as well as, for example, bounding boxes, semantic segmentation, as well as, for example, word coordinate where you can do tracking. And there are, and also we can synthesize motion blur, which happens a lot for egocentric perceptions, right? And there are more examples. So basically what we did is we create not just the motion synthesis model, but the whole pipeline where we can synthesize all kinds of ground truth data for different tasks. Okay, so just an overview of the EgoGAN. So we have like here, like the first model is a sensor placement. So here you can see it's here, and this is a visualization. And so far we have just put a camera on a human body, like on human head between the eye. But with EgoGAN, right, we could also potentially put other sensors, for example, IMUs or like this grayscale cameras for SLAM system. So there are other sensors we can also synthesize. And another component, this is automatic closing simulation. So because we want to generate synthetic data that not just one person wear glasses, there are also other people in the environment. And for doing that, we need realistic clothes and also closing simulation because other people also move. And basically what we did is use this state-of-art algorithm like this graph neural network to automatically simulate the close movement for other people in the egocentric view. And at the core of this EgoGAN is actually an egocentric perception-driven motion synthesis. So what does it mean? So there are different ways to encode like a scene or like a contextual information into the motion model, right? And for this EgoGAN, what we did is we say like the way the virtual human perceives the world is actually by egocentric perception, right? So the person move, the perception change, and then the perception change that drives the human's next movement. And by doing this, we think, I mean, we don't really prove, we haven't proved that, but we think this type of behaviors is better for generating training data for egocentric perception tasks. So the key advantage, I would say, like it's first is egocentric perception driven. And the second, I think this type of egocentric perception driven motion synthesis model can give us certain type of egocentric behavior. Right. Another thing is there is no path planning. For example, so far we try to synthesize goal-reaching behaviors. And for previous work, they also need some path planning when you try to synthesize human motion in an environment. And here, by this egocentric perception, right, we don't really need this path planning anymore. And another very interesting thing I would say is actually we produce some emergent multi-agent behavior. So this human synthesis model is trained with like a static bounding box in the environment. People move around and try to avoid the static bounding box. But actually our model later when you test it, it can work with like a dynamic environment, can work with multiple people walking in the environment. Okay, so just a little bit detail about this ego sensing driven motion model. As I mentioned, so the first thing is how do we represent the human body and how the human perceives the environment. So in this work, we use this compact egocentric sensing, like the idea borrowed from the robotics community. So basically this sensing changes when humans move their body, right? And then this defines the state. So we use the RL-based algorithm. So this defines the state. So basically where the body is, what's the environment around the human body, and as well as, for example, the distance and the remaining time and this type of things. And this is a state, and this goes to the MLP and give us then we can try to learn the policy, right? So we use the PPO algorithm to optimize the stochastic policy, and then basically we have a kind of action sampled from this, and then this action can drive the human motion, can drive this human movement. Okay, so that's a model. And I'm not going to show the quantitative evaluation here, but what I want to show here is a very interesting comparison. So as I mentioned, we kind of produce this emergent multi-agent behavior, I would argue. And this is a physics VAE work where they try to synthesize multiple agents, right, to reach their target. And we tried some experiments similar. So we try to synthesize virtual humans, right? 8 virtual humans. They try to reach their target. And these are the body shapes for these virtual humans. I mean, I think it's very interesting to see these virtual humans, they kind of try to avoid others, and then they try to reach their own target, right? They try to not collide with each other. I think it's an interesting thing. Okay, so with this EGOGAN, we showed 2 perception tasks in this paper. The first one is mapping and localization for AR. The second one is human mesh recovery from egocentric view. So this, the first thing, what is mapping and localization for AR? So for example, for AR devices, HoloLens, right? What you want to do normally is to wear this HoloLens, for example, walk around in a building, and then you want to build a structure from motion map based on this captured data. And later, this structure from motion map can be used for localization of other AR devices, right? So that's the application scenario they have. But the problem of building this structure from motion map is it's kind of sparse, and it's kind of, so you can ask people to walk in a big building, but the data you can capture is very limited. That's why you can only build a sparse structure from motion map. And with this EGOGEN, right, with this egocentric synthetic data, yes, I can do that. With this egocentric synthetic data, what we did is we can actually put virtual humans in the 3D environment, lots of virtual humans, and we can capture lots of more data. And with this more egocentric synthetic data, we can build a much more complete structure from motion map. And in the paper, we show with this more complete structure from motion map, it also improves the localization and mapping accuracy in the AR applications. So the second application we showed is egocentric human mesh recovery. So this is the task where, computer vision task, so where you give an egocentric image and you want to reconstruct human mesh from this egocentric image. So this is a challenging task because the cameras are embodied. It's very dynamic. It's lots of movement. You have lots of truncations, and there are very limited data to train a model for such task. And what we did is basically with EGOGEN, we can generate synthetic training data. So we leverage EGOGEN to generate 300K RGB and 105K depth training data of humans, images of humans moving in 3D environments. So here's just some examples from the rendered image from our EGOGEN. And with such synthetic data, what we can do is to fine-tune to first train a state-of-art, for example, regressor based on the synthetic data, and then fine-tune them on the small amount of real data. And you can see that we get 20% improvement of the post-estimation accuracy, right? So I think even though so far we have only showed 2 tasks, like perception tasks with this synthetic data, I think it's very promising. With better and better human motion model, for example, hand-object interaction model, I think the potential is, I think it's huge. Okay, so yes, as I mentioned, right, from this egocentric synthetic data, we get very accurate and rich ground truth annotations. And this year CVPR, you can also see like many large-scale real-world data, egocentric capture. And the advantage of this real-world capture is they are semantic rich and diverse. And I think these two type of data, right? One is synthetic data, which generated by some human motion models, right? 3D graphics and to render nice data. So this is synthetic data and real world capture. I think they are complementary to each other. And I think this type of data will really facilitate the learning of egocentric foundation models. And it's not just egocentric foundation models. I think human motion models like diverse, generative and effective human motion models really have the potentials to help us to generate lots of synthetic data to train all kinds of foundation models. Okay, so I present this 3 work and 2 will be presented this year at CVPR. And I want to thank my, my wonderful collaborators and also my student who are leading this project. And I want to say CoreWeave is on the job market. So if you are looking for someone who wants working on human motion synthesis, I think you should reach out to him. He's wonderful. Thank you very much.
Maybe I can try ask the first question because like testing the mic. Is it working? Yet?
I can hear. Wow.
It is. So I have a question regarding the first work where you optimize the diffusion, the noise space. Do you need to assume that the noise space is linear so you can kind of walk through it?
So it's a Gaussian, like it's this Gaussian space, right? So basically we use a standard optimization to like a Adam optimizer to optimize using gradient descent. So we didn't have any assumption of that.
Okay, thank you.
Yes.
Thanks a lot for the talk. What is your take on multi-agent sensors?
Multi-agent sensors?
Yeah, multi-agent sensors. Humans and non-humans alike. I wanna walk to the next move forward, but also my dog is moving forward as well.
So multi-agent.
What's your take? What's your take on multi-agent synthesis?
Synthesis. Okay. Yes. So I mean, I say we have this emergent multi-agent synthesis, but I think it's a very basic thing. So they just avoid each other. But if we really want to synthesize, like I think graphic community, they have been trying to do like cross simulating this type of things, right? I'm not very familiar with that literature, but I think like if you think about using like kind of diffusion model, data-driven models to synthesize human interactions, right? We need lots of data, right? Like human, when they interact with each other, they behave differently. Like it's a topic needs lots of investigation. Yeah.
How do you see that in the future?
I mean, for the application I'm interested in, definitely we need that.
Yeah.
Right. If I have AR glasses on my head, when I talk to someone, like there are social interactions, right? Lots of interactions. And if I want my AR glasses to have a good perception model, right? It has to understand like this type of like social interactions.
Thanks so.
Yeah, sure.
Professor. So I have a question regarding the Ego HMR human mesh recovery in the EgoGen. So while taking inputs from the person wearing the device, so all the parts are out of field view, right?
Yes, could be, yes.
So is there any head motion is taking into being account for calculating his whole mesh recovery? One is that, and another, are the persons right in front of him in the scenes are also being taken into account for generating his mesh?
Yeah. So if you are talking about generation, right? We don't really take like we don't have a model which kind of like, for example, this egocentric motion model, it's not trying to model the behavior of interacting. So the model is basically trying to avoid objects, potentially moving objects. It considers other humans as a moving object, try to avoid this object to reach the goal in the environment. So I'm not sure whether I answer your question.
Question was whether as all the parts of the body of the person wearing the camera, so how does his or her pose or mesh can be recovered? Is it using something like the head motions?
Okay. So the way in the test, like in our work, what we test is a mesh recovery of the person who don't wear the glass, who doesn't wear the glass, right? Is a person like that are in the egocentric image, right? To estimate the motion or the pose of people who wear the glass is another task. Yeah. Okay. Yes.
Thanks for your interesting talk. And I know that I'm interested in I'm interested in the motion synthesis, and currently there are a few methods doing this. For example, we can use diffusion model to generate motions in like continuous space, and there are also some like works trying to discretize the motion and use GPT or some other things to do that. Also, there are some like physics simulator using RL. And how do you think of this method? And like, do you have any hints, for example, what kind of scenario is like can benefit what kind of method do you have kind of insight?
Yeah, let me think. I think I constantly thinking about this question, right? There are different ways of doing that. Which way should we do? Like the solution is I have students working on different directions. So we will figure out which one is more effective, right? So far my observation is, I mean, in my group, we don't have like expertise in physics-based motion modeling, right? So that's something new for us. And a diffusion-based approach, so CoreWeave has been working on that. So I was really surprised by the quality, but when it comes to the control, right, I think there is still like a long way to go. To have like a sparse control, process control, I think there is a long way to go. And another thing is data. So far, we really rely on paired, lots of 3D motion data and text annotations. That's why we can really train diffusion models. But I think the next big thing is where do we get the data that can describe more behaviors, right? And I think the way I would try to push to try to learn some motion behavior models, not really from explicit data, but try to see how we can distill such information from diffusion models. For example, diffusion video models, which they can generate nice pixels of human movement, right? Can we distill 3D information? Can we distill human behavior representations from such models? Yeah.
Yes. Very nice talk. Thank you.
Thank you.
You showed some results about this collision avoidance, multi-agent.
Yeah.
And that's I'm very curious about. So do you consider that as an emergent behavior from the simulation, or and if so, how does it really compare with the motion planning community where we have done the collision avoidance crowd simulations and stuff like that?
I mean,
it looks really good. That's why I'm very curious how.
The thing, I mean, so the reason I show that is because it was a surprise for us. Like, yeah, yes, because we didn't train on these tasks, right? We really trained on people walking like in like a bounding box around, try to avoid bounding boxes. And when we test in these cases, you can see like it's just I mean, I can't really say quantitatively, right, how significant it is. So I put it here because it was a visually interesting observation for us, how much we can really generate by training, like by leveraging the data we have and by training like this our motion model, right? But I think it's we try to build a story on top of what we see, right? We say, oh, this person trying to avoid another person, right? Maybe they're I don't know, like but actually it's probably not like that. They just try to avoid the bounding boxes they see.
But still be very interesting to compare with like the velocity obstacle-based methods or crowd simulation-based methods, right?
Yeah, I would love to compare. We don't have that expertise in the group, but yeah, I think this is just qualitatively.
Very interesting.
Yeah, thank you.
Thanks.
Thank you very much.
All right, now we are heading the closing of this wonderful workshop that hopefully you all enjoyed. But before we do that, we have to do the announcement for the